Hey Guillaume,
Hello, how are you?
pretty good, you?
Okay, yeah, thanks. So far, so good.
Anything I should know? Or maybe I should try to share my screen or something like this to verify that it works.
You want to try? I need to give you presenter rights.
Yeah, maybe.
Make presenter, and now you should have an extra button.
Yes. Let's see if it works. Yes. Oh, look at that. Guess we're good.
Oh, yeah. And if you click on plus, you should be able to upload some presentations. Maybe, I don't know if they've been, let me see.
Oh,
Click
yeah,
present.
so I could, yeah.
Yeah, and
Okay.
I could probably upload some from the website, but maybe you have a newer version, I don't know.
Okay, first maybe I would need to finish my slides. No, I'm not far. I mean, anyway, it's a discussion, like what matters is there.
Yeah.
But I'll finish that now.
Hello, Sasha.
Hey, how are you doing?
Okay, thanks. Right, so I uploaded a presentation for the first talk. Okay, 7 a.m. LPC time. The first talk starts in 10 minutes, so we'll have a bit of time if people want to try things out. We need to go through the slides, but let's see. I think a few people are still joining. Maybe just wait 1 minute. Matrix seems to be stable today, so hopefully it's going to be smooth. Okay, let's get started with the standard slide. So welcome to the Testing and Fuzzing Macro Conference. I'm Guillaume Tucker from Collabora, and we have Sasha Levin from Google as MC leads. So we have to go through a few admin things first. Well, there's the list of sponsors. So we need to say thank you to all our sponsors who've made LPC possible this year. So we have as diamond sponsor, we have Facebook. Platinum sponsor, we have IBM. Gold sponsors, we have ARM and Microsoft. And silver sponsors, we have Amazon Web Services, Netflix, and Red Hat. And speaker gift sponsor is Collabora. The t-shirt sponsor, and I'm wearing a Fuzzing t-shirt, but still there's some t-shirts available, is VMware. And conference services, the Linux Foundation. Anti-harassment policy, I think you can read this on the main website, but here it's more to remind people that it's there, and please bear it in mind. Yeah, okay, so housekeeping. So basically everybody should have the microphone and camera muted, except when you are talking or when you have a question. So if you have a question, you can unmute your camera or microphone, and people will notice you're here. There's a hand button at the bottom of the screen, but usually that goes completely unnoticed, so it's much better to just unmute your video or sound if you want to talk. Okay. And then yeah, there's the list of planning committee. So thank you to all the committee for making this possible. And this is the we're not quite on a break yet. So now is a good time if anybody has any questions, like any problems joining or general comments about testing and fuzzing microconference, what it is going to be about. Does anybody have anything? Yep.
I'll just note that our schedule is really packed this year, so we're really going to be strict on timelines, and we might need to cut folks off. If that does happen, feel free to take it to a breakout room or continue discussion on chat or whatever works for you. This is merely a starting point for a larger discussion. It doesn't have to be the end of it.
I can't find my cards from last year with the 5-minute warning things, but we'll probably put some messages on the chat or just jump in.
So could we do a test? So have a PDF now for my slides. I'm wondering if I can, rather than sharing my screen, I could just use BBB's way of doing it.
Yes. Yeah, if you want to try to upload, you can upload your file now, and then she'll be ready just when you start. So the first talk is in 5 minutes. We have the time to do that if you want.
Yeah, well, I've already uploaded the slides, so.
Yeah, but okay.
That would be super helpful for me as well.
Yeah.
I think my talk is the first one.
Yes.
Oh yeah,
I've already
do that
uploaded
first,
yours. Yeah, I've already uploaded the one for the sys verifier, so it's already there.
Mm-hmm.
Okay. But we can preload Martin's talk as well. So the one for the first talk is this one. Is this the right version? I got it from the schedule.
Yes, I made some slight updates today, but if it's the same one, yes.
Well, I just downloaded it like 5 minutes ago.
Oh, then that's perfect.
Okay, cool. Then where's Martin? Here. Martin, you're now presenter. You should be able to upload your PDF if you want, and then you'll be ready ahead of time. You click on plus and manage presentations, and you should be able to do upload.
I see the Zoom, but I don't see a plus anywhere.
In bottom left corner.
I don't see anything. There's just download the original presentation.
I see you've put your PDF on the
Yeah.
website. So okay, so I can download that. It's just yeah, Nikolai's presentation is not there yet. So Nikolai, if you have a PDF, you can upload it, and then we'll preload it. Okay, so this one is for Martin.
I see Mara and I have the same style.
I think there was a template for LPC, but maybe nobody's using it. Anyway, what's important is what's inside.
It's very important.
Okay.
We can maybe get started with the first presentation, given that.
Yeah.
It's okay. Yeah.
So I give presentation to Mara. Okay, so now you should be able to change the slides.
Yeah, I am.
Okay, cool.
Oh, can I start?
Yep.
Yeah, hi everyone, I'm Mara, and today I'm going to present you an idea I worked on during my Google internship together with Dimitri Vyukov and Marco Elver on how to detect semantic bugs using differential fuzzing. So detecting many classes of bugs is easy due to the way they affect the system. They either cause assertion failures, crash the system, or trigger some form of undefined behavior, which is detectable using existing analysis tools. However, semantic bugs are quite different because while they make a program operate incorrectly and might make the program produce unintended output, they do this with the possibility that the program might not crash or trigger assertion failures, which makes it impossible for existing analysis tools to detect semantic bugs, and it requires the developer to go on and manually inspect and test the program. So how can we find semantic bugs? One way to do this is by using a system specification, which is a way of formalizing a system's intended behavior. And this can be used as a baseline for writing tests. However, this gets more complicated to achieve as the size of the system increases because more and more tests need to be added and they become more complex. And also, some existing large systems have no centralized specification available. So if we take the Linux kernel, for example, we can consider its specification the union of documentation found in several resources, man pages, and the implied expectations of user programs. And while there are test suites available to detect regressions, They require a lot of engineering effort to extend and maintain. So how can we automate this? One way of doing it is by using differential fuzzing. And differential fuzzing automates the detection of semantic bugs by providing the same input to different implementation of the same system and cross-comparing the resulting behaviors. And if the system disagrees, we can say that at least one of them is wrong. Maybe both of them are wrong. And this idea works quite well for simple deterministic systems, such as JSON parser, regex engines, or compilers. And since, to the best of our knowledge, there is no tool that automatically detects semantic bugs for the kernel, we want to try to do this for the Linux kernel. However, this is not trivial due to the several technical challenges that we need to take into account. First of them is kernel non-determinism, which is caused by several factors, and each of them can cause false positives in the result that needs to be accounted for separately. The second challenge is implementation-defined behavior, which occurs due to undocumented changes that get altered from version to version. And finally, considering that the input of a differential fuzzing engine for the kernel is a sequence of system call, if we take into account all the possible combinations of system calls and their arguments, we can say that the state space of the input is unbounded. Moreover, in order to make differential fuzzing useful for the kernel, we need to choose the right comparison candidates. So the right different implementations to compare. And there are several pairs that are worth discussing. First of all, we can compare an LTS with mainline, and this could be a way of preventing bugs from reaching the next release. Then we could compare different LTS releases. However, we need to be careful how far apart these are, because if they're too close to each other, there won't be many intentional differences to whitelist, but probably most bugs are present in both versions. However, if they're too far apart, we need a very thorough mechanism to whitelist all intentional differences. We can also compare minor LTS updates to ensure that bugs that are claimed to be fixed by the update are actually fixed. And probably the most interested would be different kernel implementations, for example, Linux versus gvisor, because this could uncover real semantic bugs. However, this is quite challenging due to all the false positive caused by intentional differences that we need to account for. And our solution is a tool called sysverifier, which currently provides differential fuzzing for the Linux kernel. And it's part of the syscaller project that additionally provides unsupervised coverage-guided kernel fuzzing. And the way this sysverifier works is by generating a continuous stream of random programs, which are sequences of system call that are first dispatched for execution on different versions of the Linux kernel. And then after the programs have finished executing, the programs are gathered and verified. And currently for each system call, we gather the error nodes and the information about whether the VM has crashed executing the program. And when cross-comparing the results, we find mismatches in the error nodes returned. Sysverifier creates an execution report that can be used for further inspection. I will now give a quick overview of the architecture of sysverifier. So at the host level, when the main utility is started, this will spawn several virtual machines that will each run a different version of the Linux kernel, and this can be configured by the user. And then it will start generating a continuous stream of programs that will reach a runner component on the virtual machine. And the runner component is responsible for turning the program into input to the program executor that will then execute the program, which is triggering system calls in the kernel. And then we'll gather results and send them back to the host. And when the host has received results from all the kernels, it will cross-compare them. And in case a mismatch is found, it will write a report to persistent storage, and it will also gather statistics about execution. And statistics are important in order to see the system calls that are the most problematic. both in case of true positives and false positives. And in order to establish whether the results reported by sysverifier are actually true positives, we did some bisection of mismatches found, and I'm going to present you a few examples. One of them is on the IOU ring setup. So this is a system called that operates on ring queues that share data between the kernel and the user space to avoid duplication. And on the old kernel, this system call was returning bad file descriptor, while on the new kernel, it was returning no such device or address. And bisection led us to this commit, which shows that the change was actually made. However, this change is not documented in the commit description, so it might or might not be a bug. Then an example of another true positive is for perf event open. So perf event is an event-based tool for performance and troubleshooting. And the old kernel was returning argument list too long, while the new kernel was returning a valid argument. And bisection led us to this commit, which basically shows us that the new kernel has had the system call description with an additional argument. And this is actually an example of an intentional change that needs to be whitelisted in the architecture of sysverifier in order to not cause false positives. Now, as I said, in the kernel, there are several sources of non-determinism that need to be accounted for, and I'm going to talk about several implementation details that we opted for in order to remove some of them. First, we are favoring single-threaded mode in program execution to avoid system calls failing because of a previous one that they depend on hasn't executed yet. So for example, if we have a program where we have an open and a write operating on the same file descriptor, if the program is executing concurrently and the write is gonna execute before the open, it will fail because it's trying to write to an invalid file descriptor. However, this sacrifices some true positives by eliminating concurrency. Then we want all programs to start from an initial clean state. So we create a new working and process directory, new set of namespaces, and new C groups in order to avoid false positives occurring because of accumulated hidden state. And finally, we only considered mismatches that are returned deterministically. So we rerun programs in order to eliminate flaky mismatches that are caused either by the current state of the system, by background activity, or some other factors. And sysverifier is still in the prototype stage, so there is a lot of work to be done on it. First, we want to research and eliminate other sources of false positives, because there probably are several of them. It would be super useful to provide automatic bisection of mismatches. It would be also interesting to extend the return state of each system call to include information about memory, registers, contents of disk, privileges assigned to system calls, as this would be a way, for example, to unveil memory corruption. As I said before, we could compare Linux with other kernels on a subset of system calls, or we can create an execution model of a subsystem of the Linux kernel to compare against in order to automate the process of finding some bugs in new releases. So to summarize, semantic bugs are bad because they're very difficult to find. Differential fuzzing is a way to automate the process of finding semantic bugs. And sysverifier is a differential fuzzing prototype for the Linux kernel. Below you have the link to the main repository. Sysverifier was built as part of the syscholar repository. The link will take you to a more detailed documentation also on how to run the tool and how to interpret the reports returned. And it also contains all the code. Thank you. Do you have any questions?
Yeah, I'm curious how big the whitelist you mentioned you ended up with. I can only assume there's. I'd argue that the specs aren't just the docs and the code; it's also only what users actually care about. And I can assume that a lot of changes in ernos no one cares about and they're fine. which would lead to a massive whitelist. And I'm curious how big it ended up being on your end.
So we prioritized on based on the statistics, and at the current point, in order to verify that whether a mismatch is due to an intentional change that needs to be whitelisted or a bug, we basically had to go through all the mismatches returned. We found several things that need to be whitelisted. For example, like a perf event was a tool that was a subsystem that has seen a lot of changes in the near past that need to be whitelisted. So we mostly looked at ways to get rid of non-determinism rather than whitelisting things, because whitelisting would be easier to do while, like, in the moment we integrate automatic bisection in the tool.
Hey, this is KY. Great presentation. So as part of fuzzing, what changes? The order of system calls changes, or the arguments are going to be changing across the entire spectrum of valid and also invalid arguments. So what's the space of the overall test space for the system calls?
So we use the declarative language for describing system calls that is also used by Syscaller, which gives a description of the system call with and constrains arguments to what would be interesting. In the same time, avoids arguments that we know would from the beginning would be invalid for the system calls. The language we used for generating programs is called Syslang, and you can find a lot more information on it in the Syscaller repository, because it's also used in Syscaller for generating test programs.
Okay, so actually from run to run, the programs that are generated will actually be using arguments that are different and
yes, completely random.
completely random and covering the entire space of what those arguments can take.
Yes. We can, for example, Syslang allows us to restrict the set of system calls to smaller or a larger one, depends on what we want to do. So for example, from the start, we've eliminated system calls that cause concurrency from the set of system calls that are used in generating programs.
Thank you.
Have you considered running this on like the stable trees? Because I would assume there's less noise between different stable tree releases versus upstream releases, because you kind of ignore merge windows where most of the intentional changes of that sort happen.
So we've only run it on stable releases. We've only compared stable releases between each other so far.
Oh, sorry, my headphones died. Could you repeat, please?
Sorry. So far, we've compared it only on stable releases of the Linux kernel, mostly focusing from 5.13, 5.12.15, and 5.10. Like, that's the area we've compared. We initially went to 5.13 versus 5.12 because we expected to not have many mismatches there, and most of them to be due to intentional differences. So they were very good comparison candidates in order to eliminate the sources of non-determinism that were causing the most problems.
So you said you were gathering. I'm sorry. Go ahead, Sasha.
I was thinking like between releases of the same series, so like 5.13.1, 5.13.2, and so on, and kind of just make sure that within the same release.
No, we didn't compare them as close to each other because I started going further and further until the point I got mismatches, and comparing such close releases didn't unveil any mismatches very quickly. And yeah, it also depends on what programs are generated, obviously. And you need to find the system call, exactly the system calls that are problematic in those two releases.
Thank you.
So I have another question. So since you said that the parameters are all already known to be valid parameters in the sense that no, all parameters are valid, because if the parameters are invalid, we expect appropriate error codes to come back and they shouldn't crash the system or anything. So every parameter is valid. And so now, as you have compared these various kernels, you talked about known differences. Have real bugs been identified? And if there's such a list of real bugs, can you point us to a page that lists what bugs have been actually found with this test and what we have done about it?
So we started working on the tool the beginning of June. It's in a very early stage so far.
Okay.
So we think that there still needs to be a lot of work done on the tool in order to then be able to claim for sure that bugs are actually bugs.
Okay, thank you.
Just to say, there are a couple of questions on the chat. Are you able to see the chat? Would be good
Yes,
if
I
you could
think so.
read the questions. Thank you.
It's loading. Okay. Is there some implicit specification that certain error node can be replaced by others and still consider it backwards compatible? Not supported can be replaced by any value at a later version. I'm not sure. We've like in the bisections we've done, we wanted to make sure that the changes that were causing mismatches were actually mentioned in the commit descriptions we were pointed to. So maybe Dimitri or Marco have something to say about this, but I'm not sure. Then did you already consider coverage guidance using the coverage data from multiple VMs and make the corpus grow to increase coverage on the kernels of multiple VMs? So far, we're not working with coverage. We haven't integrated that feature in differential in our tool. Maybe since Dimitri and Mark are contributors to Cscholar, they can also add more on this. Okay.
Oh, can you hear me now?
Yes.
Okay, good. So I can provide some maybe additional comments on this implicit specification. So there's none that we are aware of. Yeah, there are some obvious candidates like what you mentioned, not supported. Maybe ENO, TTI versus something else is also whitelisted, but we're not aware of any actual specification for all of those cases.
Thank you. And then the question from Martin. I understand that fuzzing is a never-ending process, but we are talking about 1 hour, 1 day, or 1 week. Most runs, because we were in such an initial stage, most runs like gave us results even after less than 30 minutes, because at the beginning we had a lot of mismatches due to false due to false positive caused by concurrency and accumulated state. And then afterwards, after eliminating those, and after whitelisting things like perf event open and disable system calls that create concurrency. For example, when comparing Linux 13 with Linux 12, we got very few mismatches. So it really depends on whether the programs that are generated are gonna cause some mismatches, whether we are triggering some source of false positives, but especially initially we got results very quickly. We never let sysverifier run for 1 day or 1 week in order to get results, because we got some useful reports way faster than that.
Thank you. Yeah, I guess the question was, how long do you think it would take to get some meaningful results in the future when the tool has been proven to work?
So depends on how much, obviously depends on the resources and how much parallelism we can get running. So for example, for syscaller, I know we can get meaningful results even within a day. So I presume it's going to be possible for sysverifier. It always depends on the amount of resources and the versions we are comparing.
Okay. Well,
because I presume that a new version with a very old version will produce results very quickly, because there, as I said, there probably would be intentional differences.
yeah, I guess the reason why I was asking this is, as Sasha was thinking, in the stable releases, as in like 5.13.x, we don't want to introduce any changes there. That would be, a semantic change. So that would be a very nice place to actually use this differential further. And so there are new releases. Let's say at first it's a couple of times a week, and then it dies down more like once a week. So that's definitely doable to run something for a day and try to catch something. It's like a last effort, really last thing, to try to find differences and review them. So yeah, that's very good work, and that could be very, very useful.
We have 2 minutes left before the next talk. Thank you.
Mm-hmm. Have you considered any other metrics to measure behavior other than the syscall errors? So there is some syscaller internal flags that we worked on, which were a good indicator, especially in the concurrency aspect, to see whether a system call has executed or not. Because, for example, if we had the write followed by a read and the read was taking place before the write due to concurrency, we could clearly see that, for example, the system call would block in case of a pipe. Other metrics that would be useful could appear when we extend the return state. We've considered checking whether a system call alters memory in the same way by looking at the memory area in our discussions, but we haven't gotten so far.
Hi. So we considered using some other things, as Mara mentioned. The good question is if we actually need to do this or not, because other things can also be sensed with system call return values. For example, if there is, I don't know, an additional file on the disk, then calling open on that file in the program will return different result if this file is present or not. So potentially all of the other things can actually be sensed by looking just at the system call return values. Yeah, but potentially using other things may increase efficiency. Maybe that's a good research question.
Okay, thank you. It's now, sorry, but it's now time for Martin's talk. I guess we can continue discussion on the chat or in the hacking room if you want to. Martin, are you ready?
Yes, I am ready, and I think my webcam is ready too.
Okay, and thank you, Mara, for your talk. That was great.
Okay, so I'm going to talk about bare metal testing and why containers could actually help increase testing. So my name is, wait a second, Martin Rokala. Some people might know me under Martin Perez. I just got married this year, and so a lot of people are not aware of this for good reasons. So I'm now a freelancer. I used to work with Intel before, and I am a Valve contractor. So I need to get used to this. So I am very active in the graphics subsystem. I used to be on the Xorg board of directors, and my focus at first was on Nouveau, the NVIDIA graphic driver, then Intel, and then AMD. So my mission is to get production-ready upstream Linux. That means that any new release of Linux will be runnable in production in any system. So basically, we want to make sure that there are no regressions, and automated testing is a very effective way to do this. So my experience on this has been with Intel graphics, especially, where we are running an integration testing test suite called IGT that is, it's integration testing, so there's a lot of false positives and things like this. And so I wrote a tool to remove false positives, to document what are the known issues and address so-called flakes. So that means that you run the test suite twice on the same kernel and you get different outputs. And that can be due to concurrency or any other things. And then I also have written a tool called EasyBench that is an auto bisector for performance unit tests or image changes. So if you run, let's say, a graphic driver and you run a trace of a game, you want to make sure that the game looks the same. And if the output changes, then you want to bisect that. So EasyBench was doing this, and I'm working again on making something like this for Valve. So why do we need to care about rootfs generation? So if you really want to prevent regressions in Linux, then you really need to run a lot of test suites on a lot of different hardware. So you want to make it as easy as possible to run these test suites. The problem is that we have different hardware in different CI farms, so there's no one farm to rule them all that would have absolutely everything. So that's one problem. And then the different CI farms have different interfaces or requirements on how to run, how to run tests. So, finally, if we were to reboot the test machines every time we want to run a new test suite, that might be taking a lot of time, or at least wasting valuable machine time, just because we didn't want to make one rootfs with absolutely everything, and we instead have one rootfs per test suite. And yeah, so for graphics, we have a lot of different test suites, and the dependencies there are also very tricky to get, and maintaining a rootfs is not a trivial task. It's not just install this package. So that's a reason why making rootfs generation as easy as possible is a good idea. And yeah, basically, since we want to run as many test suites as possible in a CI system, we want to make adding new test suites as easy as possible. And now we're going to go into comparing the current way of doing, basically of deploying new tests, and what if it were used by an OCI container or deployed using OCI. So I call rootfs the traditional method of deploying the test environment. And then The OCI container is usually found for unit testing, and in the web world, when I say unit testing, I mean like GitHub Actions or GitLab CI. When you run tests, you are packaging your tests as a container, or at least the tests run also in a container. Then, so for the rootfs, they are usually created using Yocto, buildroot, or kernel CI rootfs tool. It can be also DebOS, Virtual Builder. There's a lot of tools on the OpenCI, Open Container Initiative containers. We have Docker, Podman, or Builder. Docker was the original one. The others are, well, also pretty good. Then one big difference between the two is that the rootfs is generating a self-contained full disk image, which means that if you need to flash this image, you need to reflash absolutely everything. You don't do differential flashing, for instance. And the portability can be a bit bad, because if you have multiple boards that have different requirements for modules or firmwares, then well, either you make one rootfs that has absolutely everything, or you'll need to make one rootfs per device that you want to boot. Whereas, so with the container side, that's the biggest difference. Instead of generating a full disk image, you have a set of overlays. So that means that, for instance, you can have as a layer your base Debian system. Then on top of this, you have the dependencies for running any graphics workload. And then you can have as a last layer, which test suite you want to have with the latest version of it. And this way, if you have two containers that use the previous two layers, then you don't need to retransfer them because they are already on the device. So that means that you don't need two full disk images. And so because of this, it is faster to deploy, and it is very portable because basically there's no platform setup. The platform setup needs to be done before, which can be viewed as an inconvenience, but we're going to see that it's not necessarily that bad. So an additional point is for containers is that you already wrote these containers for unit testing in GitHub or GitLab. So why not reuse that for bare metal testing? That would be very useful. The problem is that how do we boot to a container? Since, as I said, we need to have initialization of the platform, for instance, setting the network IP or setting the time, mounting the drives for storage. This sort of thing needs to be done. So do we need to make another rootfs just to be able to load containers? Well, not really. I've been working on this tool for quite a while now. I mean, basically this year. It's called boot to container. And what is it? What it is small initramfs that you can easily pixie boot. So that means network boot. It has a declarative configuration using the kernel command line, and there are quite a lot of features. So first thing is, of course, containers require internet access. So DHCP and setting the time using MTP is important. Then we can store the, well, basically we have a cache drive that can be used for caching the layers, but also caching data that is used for testing. And we can have auto selection of the cache drive, auto formatting, and we can also select a swap file, or say that I want to create a swap file of this much and mount it, or not mount it, but swap on it. And then you can create volumes. So container volume is a bit like creating a partition. And so one interesting thing that we can do with boot to container is that we can sync the content of so-called bucket from, let's say, Amazon S3 or anything compatible with it. And you can basically download files to the drive of the machine, run your test, and then sync back these files to this Amazon cloud or anything else, Min.io or something like this. And it also supports local encryption. So If you want the files to remain confidential on your test machine, you can. And only if you provide the key, the FS script key, then your job can access these files. Otherwise, well, it's just encrypted blobs. And finally, you can also specify an expiration, so you can say when you want the files to be deleted. So that's practical. And it's time to give an example. If you want to run the IGT test suite that I was mentioning before, using this tool, this init from FS put to container, here is the entire command line you need to set. This, of course, is like it's a template, so you would need to actually write these values, but then this can be auto-generated by your infrastructure. So let's dive right in. So here we say that just select a cache device. Like you could say that I want to use dev as the A1, but here it's just like pick anything, I don't care. Then for NTP, it's the same. You just say use like the auto NTP server. So yeah, whatever. Then let's not look at this line just yet. Then we say, I want to create a volume. So volume was like a partition. I want you to mirror from a place called job, which is defined here. So job is just a nickname or an alias from a cloud storage at this URL using this username and this password. And so then we just say like, well, so from this endpoint, we want to use the bucket name for the job. So this is, again, something that is usually randomly generated. I want you to pull the data from this job bucket at the beginning of the so-called testing pipeline. And then every time there's a change that is happening on the file, I want you to push it to the job bucket. So this way we can see if the machine crashes, we can have intermediate files. And then I want you to delete this mirror, this volume at the end of the execution. Very good. Then there are two B2C container parameters. Basically what it says is, first I want you to run this container and then this one. And then for the people who are used to running Docker or Podman, then basically this is the Podman command line, and same here. So for this one, this is an example. In our case, we verify that the machines are in the state that we are expecting them to be. So this container is just going to check that it is the case. And if it fails, then this container is not going to be run. But if this succeeds, then the next one is executed. And we say, hey, I want you to use the job partition or volume, and I want you to mount it in /results. Then here is the address for the IGT container. Then I want you to run the IGT runner command from this container, and I want you to write the results to /results. And that's it. This is literally how you run a test suite. And then the console and all this is just a way to output things using a serial console. So if you want to add another test suite after this one, well, just add another B2C container command, and you don't even need to make the container yourself. As I've shown here, the container is just the upstream one, and we can use the same one for unit testing or the real hardware. So one issue that we found out with containers is that if you have a very limited amount of RAM, then that's not going to work too well, because generally it does use a bit more RAM, and same with storage. So generally I would say, like, if you have less than 64 megs of RAM, then that starts being a little bit problematic. Although Podman is not too bad in memory usage if you're using crun rather than runc, but which is what I'm doing anyway. And then I have more open questions. So now that we could be sharing the containers between the different CI systems, we would also need a way to report these results in a standardized format, so we can, well, basically run this standard test container in any form we want and get the results, and then it doesn't really matter, where the hardware is. We can queue work anywhere. So there is such a format that exists already. It's called GUnit, but it's more like for Java testing. So the output is like the logs, for instance, collected, or just std out, stdr, but then kernel logs are like, not really. So this is something that that could be added there, or I don't know, like we come up with our own system, our own format or something like this. And that is it. Thanks for listening, and I'm waiting for questions if you have any. Thanks, Guy.
Hi, Martin. I have a question on the kind of the early boot part of boot to container. How are you handling devices that need, for example, modules in a RAM disk before actually even having networking and stuff like that? Because obviously you need networking for all this stuff to work.
Yes, very good question. So I have been cheating, and basically the kernel that we give is already having everything built in, including the firmwares. But I have a to-do to basically have, well, I guess anyway. Well, I guess we have to anyway have the network firmware and the network driver built in. But after this, all the other modules could be downloaded as a volume. So you would specify in the boot to container kernel command line, say, I want you to mount this firmware volume, and then this module volume, and then load these modules at boot. So that could be a way to share the same kernel, but not have everything built in your kernel just because you want to have you want to boot on literally the entire world. So that's the current solution that I have.
So for kernel CI, we have a kind of a minimum Debian RAM disk that can actually have modules in it and then essentially do a pivot route. So I wondered if boot to container might be a project to kind of standardize on such a RAM disk as well, because that would be needed for the variety of hardware that would want to do this on. It could be needed.
Yeah, so boot to container is based on uroot or microroot. So this has been very easy to work with. Right now, most of the code is a shell script, but we're planning on rewriting it in Go because shell scripts. And we want to have a bit more control on what to do in case of errors, but we're not really good Go programmers, so we just went for let's get something that works, prove that the entire pipeline or the entire infra that we had envisioned can work, and then make new versions that would be more reliable. But so far it's been pretty reliable, and we have both integration testing and unit testing there. So yeah, regressions are not really happening.
Okay, thank you.
So you're welcome. Thanks, Kevin. We have a question from Shoragan. How do you push the kernel command line to the test devices from the GitLab CI run? Well, that is a good question. So if you're using PXE, so basically network boot, you can say, so let's say that you're using iPXE to boot, then you can have a DNS mask running in a server that will serve iPXE over the network. Then you're going to have the BIOS or your firmware basically loading this, and then iPXE is then going to query the configuration for the machine. And what it downloads is basically a script, and the script is saying where to download your kernel, and it's HTTP, so you can download through HTTP. Same for the initramfs and the kernel command line. So that's all you need really. and how to set it up and how to share things, how to share the machine between different, well, let's say CI systems or different jobs. This is the job of so-called the valve infra, what we've been working on. But I didn't want to get to it because we didn't have that much time. But if you're interested, definitely hit me up. I'll send you all the links. But basically, it's normal net boot. There's nothing crazy here. When you net boot, you can say what kernel, what initramfs, and what command line you want to use.
I had a question, if that's okay. Maybe you covered this in your talk already. I was sort of following other talks because there's so many interesting topics today. Just wondering if you had plans to integrate this feature into QEMU, because I think that that would be incredible. Oh, you do?
Well, I didn't have to do it. Someone else did. So at FreeDesktop, freedesktop.org, there is a project called CI template, and so they've been using QEMU a lot to boot containers. Or actually not to boot containers. They've been using QEMU to do some testing, but then they had to create their rootfs, and it's been a pain. And so they are now working on using boot to container to basically standardize on using containers for testing everything. And so the integration is not that complex. The only thing that is a bit weird compared to a normal machine is if you want to share files to the guest, then basically you need to first have boot to container partition the drive for you, then you mount the drive, then you copy your files, and then you unload and then you start again the machine. It's not very nice, but if you know like what is expected for the storage, basically it's just a label and a partition. If you do that on your own, then you don't need to make this dance. But yeah, the goal is that for freedesktop.org, if you wanted to do testing using QEMU and containers, then it would be basically you just say in YAML, I want to use this container and I want to use this QEMU configuration, and that's it.
Oh, that's fantastic. Good
Yeah, so this is the work of Benjamin Tissoir. So Bentis, if you're aware of FDO, then you probably know his name already. He's one of the amazing admins there.
Thank you.
You're welcome. Good question. Okay, so Brendan, suggesting, not a question. You mentioned test reporting format. We, other testing framework, are working on standardizing around a flavor of tap called KTAP. Okay, well, thanks, Brendan. I'll definitely look into it. Oh, and Matthew already has some concern. I mean, this was not a problem before because we could, I mean, the rootfs basically was preventing getting there. But if we can just run any container, then indeed that's the last thing. And then all the idiosyncrasies of how to run tests in different farms could probably just be abstracted away and be like, well, you put that in your container and you output this file and you put it in this place and that's your results. That would be lovely. So Kenny is saying, you've mentioned test containers a lot. Beside the one listed in your command line example, is there a list of public containers somewhere? Ooh. I'm not aware of, but that's definitely our goal. So I can talk about graphics. So IGT is one, and they are definitely the trailblazers. It's been working very well. Then for Mesa, the graphic driver for Linux in the user space, it's there are a lot of containers already that are running, but then you see this bare metal is using rootfs generation, usually based on dbootstrap. But then this is something that they potentially would be interested in replacing in favor of boot to container, but that's well, a bit more in the future. So what I can say is that for Valve testing, this is generally what we're going to be doing. So there's going to be basically running games in containers. That's a little crazier than probably most kernel developers are going to be thinking about when they write their test suite, like XFS tests, for instance. And the output is a bit more complex than looking at the Airno or something. It's frames and comparing frames and all the fun with doing that. Okay, so Kevin is asking, where are the codes, docs for boot to container? So I put this in a link, but you would have to basically download boot to container. It is there. Off the top of my head, I think it's gitlab.freedesktop.org/mupuf/boot to container. I'll post a link in the chat after the talk.
You can also, anybody can download the PDF with the arrow at the bottom left of the slides from Big Blue Button.
That too, but Kenny sent a link. Thanks, Kenny.
We have 4 minutes left. Thank you.
But definitely have a look at the boot to container README. It shows a bit more versatility than just the example I gave. There's, for instance, one thing that we are very happy with is this mirror condition. Here there's only one, but you can have multiple ones that you can specify. And I mean, I think the interface has been pretty nice. I generally agree with Matthew on why reinvent a new specification if gunit.xml exists. I think gunit will need to be extended to support dmesc message, but otherwise, I mean, I don't see any reason why not using this. And there's even support for frame, so you can have screenshots of how things are looking, which works for me. So Kevin is asking, do you track a set of kernel kconfig options that are required for a kernel that can run B2C? Yes, yes, it's painful, but they are there in the README. If you scroll down, you have anything that you need on top of the default x86_64 default config.
Hi, I just had a quick question. You noted that it can be very painful to have to flash new kernel or rootfs onto some images. Did you look at kexec as a way of avoiding needing to flash a kernel?
Yeah, I mean, in a way, kexecing is a bit like having a side loader, or not side loading, but basically another bootloader. So that could be a solution, but then I don't know. I just see it just like booting using IPXE, so I can choose basically what kernel I want to boot. And but yeah, I guess it's possible to just boot a normal Linux, a normal user space, and then download the kernel that you want to boot, and then boot on that. It's just that it's not needed nowadays because uroot or IPXE or anything else can do it for us already. So this is what we're using. So one benefit of net booting everything is if a cache device becomes corrupted or something, then we can just have it automatically reformatted. So that's pretty practical. We don't have to reinstall a test machine just because there's been a corruption in memory. This is not a problem. The best part is no part, right?
Thank you, Martin. It's now time for Nikolai and his talk about KCIDB. It's been a really good discussion. Thank you. Nikolai, are you ready?
Almost.
Okay.
Okay, well, hi everybody. I'm Nikolai Kondrashov. I don't have controls for the slides at this moment. I think.
Sorry, I'll give you this right now.
Okay, perfect. Now it should work. Okay, so I'm Nikolai Kondrashov. I work at Red Hat as a software engineer at the CKI project. I'm also a KCIDB developer and maintainer at Kernel CI project, and I maintain my Digiman project from time to time, and I do electronics and embedded as a hobby. So slides have links. If you download them, you can click them and see more regarding that slide. And also each slide can have this little blob at the bottom. That means that this slide is talking about the next release of KCIDB. It's not released yet, but hopefully going to be released soon this autumn. So a little intro. So you know that there's lots of testing systems that test Linux kernel, and each of them has their own dashboard, and each of them has their own mail report. And having all these takes time from test system maintainers and developers, and also from kernel developers and maintainers, because you have to adjust to each of those, and you have to review each of those and jump between them, and they arrive at different times, etc. So a few of us just thought, well, we can try to unify that, have some unified protocol and the system and the database for collecting all those different results, aggregating them, and then having a single dashboard and having a single kind of email that's going out when needed. So we call this system KCIDB. Kernel CI is still having their own our own native tests running on the various labs across all the world. But there is also now a KCIDB database which takes data from testing systems which want to use other software, not kernel CI software, and that would be Linaro Tux Suite and Red Hat CKI and Gentoo kernel CI ARM testing and Google Sysbot, who have been here before earlier. And of course, the native tests from kernel CI also send their results to KCIDB, and they're all mixed together there. A little closely, KCIDB structure is very simple. There is a message queue, I'm sorry, that's Russian, where submitters are sending their results in JSON, and that gets delivered to a database which you can view in the dashboard. And there is also a monitoring system which looks at what's coming in and what's already in the database and generates notifications with reports based on any number of conditions. So right now we are getting about 100,000 separate test reports per day, and around 10,000 build reports, and we're receiving about 100 different code revisions of the kernel. We have a dashboard which you can check out on the link below on the slide. It has been relatively recently updated to have a little bit more features, but this is the dashboard for the current release. I will have to redo it for the next release a little bit. We have a bunch of command line tools which we use to maintain the system, and also those can be used for sending data to the system and querying it from there. We have a Python 3 library which, if you want to integrate more closely and submit the data from Python or query the data from Python. We are sending proof of concept reports, which are getting a little bit too big, and so we are going to be replacing them with a different format. Will be shown later. We also have an implementation of a dashboard by CKI, my project at Red Hat, well, our project at Red Hat, and it's done using extended KCIDB protocol, using the facilities for extending the protocol and the schema in KCIDB. And apart from just the features similar to the current dashboard, it also supports tracking and marking known issues and masking them out if there is a bug reported and we know about this issue, so we don't fail our tests unnecessarily. So I'll briefly go through the I/O schema, the schema that is used to communicate with KCIDB, to give you a little sense of what data is already there and what's coming. So there's just three kinds of objects in the database. It's the checkout, a build, and a test. And these are main fields for a checkout object, and the only required fields are on the left is the ID and the origin, and the rest you can add as you get the data available in your testing system, and you can pick and choose to make it easier to start. The build has a similar number of fields, and it has one more required field, checkout ID. And the test results are also here. As you can see, there are not that many fields, and even those you don't have to send. And this is a work in progress, of course. We are iterating on what we need, and this is already a fourth version of the schema, and the links to that schema are below. So I would like to make a poll if I can figure it out how to do this. Okay, I'm not sure I can figure it out. Guillaume, can you give me a hint how to make a poll?
Yeah, if you click on trust, normally you should have.
All right. Yeah, thanks. So, oh my. Okay, this is too complicated for me right now. I don't want to spend too much time on that. But basically, I wanted to know if there are any test system maintainers here at the presentation. If you can just drop a word in the chat, particularly those who we don't receive data from yet. And if there are any actual kernel developers or maintainers here. Yes, Dmitry is here. Well, we received data from you already, but we would like to receive more, of course. Oh, yes. Odor. Yes, cool. Cool. Okay. Then I'll have to do the complete presentation. Okay, let's go. And yes. So the submission interface is rather simple. If you use shell, you can just pipe your data, your objects one by one into a command which has just a few options, and off you go. So once you send the data, it's there. You don't have to go back there and like get IDs for sending or anything. It's just, you can just throw the data there and be done with that, as long as it complies with the schema. That previous example just sent an empty report to the database, and this one does the same, only using Python 3. Then here's an example of, I think it's a complete module from kernel CI backend, which talks to KCIDB and sends results there. It's just 265 lines. And here's the Gentoo kernel CI well, support for KCIDB. It was taken a little while ago, so maybe now it's bigger, but at that time it was 193 lines. And here's the syscaller interface written in Go, and because we don't have a library in Go, it talks directly to Google Cloud. And it's 186 lines. We have a how to start submitting the data, and we have a separate playground with the dashboard and the database where you can experiment with sending your data without messing up anything or worrying about anything. So we think that developers should be in control of the data they receive from our database, and so we are implementing the system of subscriptions and notifications where you can pick and choose what you want, what conditions you want, and what data to send. Here is an example of a simple subscription, very basic, using stock reports, which are coming next. So here's an example of a report we are working on right now. It's basically saying, updating you about the status of a revision checked out from this repo, and at least who checked out that revision. Then it also displays all the build information. So there's one build failed out of 859 builds recorded, and that's ARM all no config build. And also list who sent the builds, and then there is a summary of the test results. 15 tests failed. We only list like 5 top failures, and then there is a link where you can go and check out all the details if you want. So I would like to ask if there are anybody who are still not sending the data to us. What would make you want to send your data? Okay, please just speak up or write in the chat as you wish.
Yeah. So at the File Systems mini conference, we were comparing notes. All of the major file system maintainers that were there, XFS, Btrfs, ext4, we all have our own infrastructure for running XFS tests. One of them was using KVM XFS tests, but I think then he switched to his own. But we all generate JUnit XML files that have all of our test results. And the one thing that we are all missing is essentially dashboard functionality of the form. You know, we're running tests daily, sometimes multiple times a day. And right now we are eyeballing summaries to discover when a test has started failing. We have a bunch of tests for a number of different configurations that always fail because we just haven't gotten around to it. I run ext4 with 12 different configurations of the file system config. So it's XFS tests in 12 different combinations of file system mount options, format options, etc. And what we all badly need is a way of being able to be told, this is a new failure, right, as opposed to a known failure. We have a bunch of tests in some configs that always fail, and we haven't gotten around to fixing it yet. And if there are flaky tests, being able to report this test started to flake as of such and such a time, and it's flaking 20% of the time or some such. Some kind of graphical dashboard that shows that would be super, super interesting. I've looked at the kernel CI dashboards, and it doesn't look like any of the dashboards I've seen have that sort of functionality. A lot of them seem to assume that they prefer that the test be 100% green, and if there's a single test failure, it turns red, and you're supposed to scramble to fix that. But we live in a world where, like I said, I run 12 different configs through ext4. XFS probably has a half dozen or more, and some tests just always fail. So we need a way of saying, yeah, that's a known failure. So don't make that turn the dashboard red. But when we see a new failure, that's what we really, really are interested in, because we want to fix the regressions. And that's sort of the requirements we're all looking for. And we were actually saying, yeah, we need to find someone to help us build that, because none of us are test engineers. and we really could use something like that. So I come bearing requirements. I don't know if that's inside the scope of what you're doing, but if it is, that would be wonderful.
Yes, thank you, Theodore. Something like that is on our horizon. We are still not there, of course, but there is something done, for example, in CKI dashboard, and that's one of the things that I would like to copy some of that at least. And I think that is, of course, valuable, especially in when the number of tests goes way up. And I think that this is basically a requirement for a database like ours, which already receives like 100,000 test results a day. So thank you very much. That's something I think we definitely should do.
Yeah.
Can I say something to Theodore? Because basically what you're asking, Theodore, is what I wrote for Intel. It's called CI Backlog. It's an open source project that is indeed a database, and it tells you not indeed it doesn't care if everything is green or not. What it cares about is regressions and changes, and every failure needs to be documented in a bug, so you can then have you can see the occurrences, the occurrence rate of the bug, when it was seen in which configurations on which machines. And the way you create these filters to say what the bug is catching is which test it came, or it was seen on, or it can be not yet a regular expression on that, but at some point, yeah. Which machines, or machine tag, if you want to have like generally x86 or ARM, for instance, that tags that you can put on machines. And then you have regular expression on std out, stdr, and dmask. And if the list of all of this is being matched, then this is a known bug, and this is filtered out. I'll send you a link to a presentation I gave about this, and you can see if this is what you want. And I believe it is, because this sounded very much like what we needed at Intel for getting IGT running on 100+ machines and 3,000 tests and integration testing all the way in graphics. Nuts. So
yeah, that sounds great. I mean, we have order 500 to 1,000, depending on how many tests get skipped per file system config. Multiply that by 12. In the ideal world, each of these tests generate a huge tarball with test artifacts. It'd be great if when you clicked on a test failure on a particular test run, you could actually download the test artifact. But that may be asking too much, because now we're actually talking pretty serious amounts of storage. But part of it is that at work we have proprietary systems that do all of this. So I know what is possible, and it's just I'd love to find a way to do that in the open. So yeah.
I'd like to add 2 comments about kernel CI. So the current front end on linux.kernelci.org shows regressions. So it's already, if something has always failed, it shows it, but not in the same way as regression. So that's already one way to find issues. But it's not as advanced as what Martin has said. The other thing is we are now gathering user stories or requirements or ideas about how people would want to work with a system that reports errors. So any ideas like the things that Ted has said, or maybe ideas from Martin's work, it would be really good if you could write this down in a shape that we can reuse. So that there's email thread about this. There's a discussion on GitHub. I'll put some links on the chat. The idea is to create a new front end for kernel CI to collect results from all the test systems, and also have a web interface, and maybe also emails and other ways to communicate with it, like command line tools, APIs, to have all this kind of user experience based on all these different user stories that people have. Thanks. I think we have 6 minutes left, so there's still a bit of time for questions, discussion.
Yes, thanks, Martin, and I will check out your presentation as well. And one of the questions that is difficult to well, for us to answer is what to do if you have a failure in a single test that is known and another one that is unknown. Do you fail that test? Do you notice? I guess you cannot notice if there is an unknown issue.
No, if something is unknown, it's considered as a regression to begin with.
I mean, like you grab STD, like you search for patterns in the output, right? So you found, you got your results of the test. You found the pattern in the output. And you say, okay, that's a known issue. But later it turns out that there was another issue as well discovered in that test.
Yeah, so there could be, indeed, if you start having multiple bugs, you might not catch additional regressions. You can sometimes, but not always. And yeah, that's a limitation that, and I mean, to be fair, there are ways of potentially detecting something else, but it requires a bit more thinking about the filtering and how you want to do this. This has been sufficient for INN15, which I mean, the driver is insane. But there are ways to improve on it. It's just that from a user's perspective, a filter is already something that is a bit remote, and people looking at the reports might be being like, oh, well, I don't know, like, it seems a bit magical, even though it is so simple. Having talked to 100 plus engineers using this system, they have been like, I have no idea how it works. Even though they have access to a website where they could see the list of bugs, which platforms is affected, what is the reproduction rate. I mean, CI probably is not bad. I'm going to pat myself in the back here. I mean, it has been allowing testing the kernel, doing integration testing, which is something that is tricky. But there are ways to improve on it. But generally, we found when there are like two bugs basically going on top of each other. And well, at some point, there's a limit to what you want to do. Documenting is great. Fixing is also helping.
All right, thanks. So I gathered that it's a fundamental problem with accidentally masking unknown issues, but yeah, and the regular expressions are of course magic. There's no question about it.
Well, they're magic, but this is something that you discuss in a bug. What should be the filter? Like, what should the filter look like? And every time someone changes the filter, it posts a comment directly on the bug. So it's not completely, like out of the blue. I don't know how the association is done, and the filter is actually, it's a domain-specific language that we created that basically is an SQL query. It looks much better than an SQL query, but it is an SQL query in the end.
Okay, thanks. I'm afraid we are running out of time, so I'm going to ask one more question from kernel developers and maintainers, and perhaps answer in the chat what would make you want to access that data and look at that data or receive those notifications from us, or subscribe to those notifications, and what would prevent you from having any use out of this? What would stop you from using it? So if you can just send me a message in the chat. Okay, otherwise I assume we're running out, so if you want, you can. Okay, I lost control of the slides. Anyway, you can reach us at kernel CI channel on LibreChat, and we have kernel CI at groups.io mail list, so you can find us there. Thank you.
Okay, thanks, Nikolai. Maybe you can put contact details in the chat.
I think that's not the slide deck. That's actually the
Oh,
the,
yes.
the thesis to it. But
Right, it's the file I got from the website.
yeah, there are two files in there.
Okay, give me a
One
second.
is the bachelor thesis. Yes,
I'll give
that's
you
good advertisement for reading that.
I'll give you
yeah.
presenter rights, so you should be able to upload the file yourself, if that's okay.
Okay.
Yeah.
I can't see it yet.
Okay, now you should have
There we go.
with the plus button, you should be able to do manage presentations and upload PDF.
There. Okay, so I think you should be able to see the slides now instead
Yeah.
of the bachelor thesis. Okay, so we'll get started here on some food for thought. Basically, the bachelor thesis from Mete Pollard, and we were testing some kernel implementation against an verified oracle. Let's see if the slide control works. There we go. Yeah, Mete.
Yeah, so let me just introduce myself. As Lucas said, my name is Mette Pollard, and I'm an undergraduate at the Technical University of Munich, and I'm specifically interested in the development of high assurance software stacks using formal verification.
Yes, and my name is Lukas Pulvan. I did my PhD in formal methods, working with theorem prover Isabel. Talk about that later. During my PhD, then switched to industry, and since then I'm interested in Linux-based systems and in the safety argumentation around them. You might have heard of the ELISA project. Other than that, I clean up stuff in random places in the kernel. And so what motivated us to this work that we'll show you is basically that you have the problem that you want to increase confidence in the correctness of some implementation. And you know that, of course, the higher the confidence you want to get, the higher the engineering effort. So on the lower left corner, you find unit testing, right? You write a few test cases and hope it just is good enough to find the bug. On the top right, this is the other extreme. You really verify the existing implementation. So you model all the details in C in a theorem prover, so a dedicated program for that. You then create a proof in that prover for that implementation, and you know that that program is correct without even testing it. Of course, that is highly complex, doing a mathematical proof. Plus, you have the complexity that any performance optimization you do, you have to provide a proof of that. So we're looking at a alternative where we are kind of in between those two extremes, and we want to test against a verified oracle. So we have a implementation that is without performance optimizations, and we verify that. And then we show equivalence by testing of the implementation that we're really interested in against the one that we verified. And that gives you a middle ground in confidence of correctness and the engineering effort you're looking at. So what did we do specifically in our concrete example? So we used Isabel. Isabel is a proof assistant theorem prover for formal verification. So a human writes a proof, and the machine checks that proof based on logical rules. We have the fortunate situation that the Isabelle developers already verified a red-black tree implementation in Isabelle. So we have a verified test oracle. And we have the convenient situation that kernel developers made a red-black tree implementation in the kernel. That's the implementation under test. And we did the last step of that. We just test the equivalence of those two implementations extensively. And I think with that, and Mita is going to tell you more about the details, how we do that.
Yeah, exactly. But I don't think that I can switch the slides. So it would be nice to have presenter rights. Or you have to do that, Lucas.
I can jump ahead and then Guillaume can give you presenter
Okay.
rights.
Yeah, so this slide is important. It shows us the whole testing pipeline, and it's composed of 6 components. At the top, you see the so-called test case generator. So as Lucas said, we want to test some test cases on the kernel red-black trees and on the verified red-black trees. So these are these 2 ones. And then we want to compare them. So, and for that, of course, we need some test cases at first. And the verified red-black tree is generated by exporting it from Isabelle. So that was the proof assistant that Lucas mentioned. And on the left side, we have like the kernel side. We somehow need to export or make available to user space a red-black tree instance, but that which uses the basically the kernel implementation. And I did this by just using a kernel module that that exposes 2 files on the debug file system, and we will dive into that shortly. And in the end, we obviously have to compare the red-black trees and see do they both equal, or are there differences, and if so, are these bugs or what is happening here? So let's start with the easiest component, the kernel part. So what I did was basically exposing 2 files on the debug file system. The comment file is used for retrieving the current tree, so reading from it prints the tree, writing to it reset, so writing a 0 resets the tree or just returns a new empty tree, writing a 1 inserts a new key that was previously specified in the other file, and writing a 2 deletes the specific key. And that's actually sufficient to test like the core part of the red-black tree implementation, so insertion, deletion, and we have a kind of printing the whole tree. Of course, in the kernel implementation, there are some more functions, some auxiliary functions, but for our purpose, we concentrated really on the algorithm because this is also the one that was formally verified in Isabelle. So the interesting part, obviously, is how do we actually obtain a proof for a data structure? So in our case, this data structure that was proved by the Isabelle developers is in a functional programming language called Isabelle Hall. And it's basically a purely functional programming language. If you are into functional programming, then you might know what this means. And in the end, there's like a strong relation between a function in the way how computer scientists understand them and how a mathematician understands them. So we can use the same methodologies as a mathematician would use. So I won't show you the proof because it's rather complex, but if you're really interested, there's an online link that you can follow and just read some of the proofs if you're really interested. But But just to give you some intuition, for example, how actually a data structure in a functional programming language looks like. So this is actually the whole code for the red-black tree insert function without the type definition, so without what is actually RBT. So the one thing that that I want to highlight here, the important thing is that in the end, even though if you're not really into functional programming, in the end, these equations that we see here are really just mathematical functions. So we can just use standard proof techniques. That is, we can use induction, we can use case distinction, we can use name it, we can use direct proof. Yeah, because everything on the left, on the right, just depends on the left. So that's how a mathematician would understand this. And in the end, we can export this Isabelle code, which was then verified later on, to a programming language like Haskell. So we can actually build our tooling around it. So this is in the end what this verified executable RBT component is telling us. So in the end, we do have to compare these two trees after applying a test case on them. And quite interestingly, after inserting the elements from 1 to 3, the Linux red-black tree produces a different tree than the verified one. So the question, of course, now is, did we find a bug? And the answer is no, we didn't. The problem is that there exists some ambiguity in the specification of red-black trees. So they're both valid red-black trees. And because of this ambiguity, there can exist more than one variant to implement these red-black trees. And in Isabelle, we know we have verified 2 different variants, and there exists one more that was not verified. For example, left-leaning red-black trees. They're quite similar, but not exactly the same. But we didn't know this implementation the Linux kernel was using. It's another variant. So the question now is, how do we deal with this kind of ambiguity in specification that is still valid and that still produces on the Linux side valid outputs? And we basically have two possibilities. The first one is that we export and specification on an executable specification from Isabelle, and that we then check the Linux red-black tree against this executable specification. But from the performance-wise point of view, this is not really what we want. What we actually want is really just comparing these two trees and see if they're really equal. So another way is obviously proving that this implementation, or the variant that that Linux is using is indeed correct. And at least for the insert function, that's what I did. So I translated the C variant or the C algorithm into the functional one, and based it on the original proof. And it took some time, but in the end it worked out. And we can say that if we assume that my translation was correct, then also the Linux variant for insert, RBT insert, is also correct. So the last part is obviously the test case generator. I implemented 3 different strategies for generating test cases. The first one is really a purely random test case generator that just suggests insert and deletes and applies them on the kernel and on the verified implementation. The exhaustive one is a bit more interesting. We test all values within a small scope. So, for example, we can say test all possibilities that make sense from 1 to 3, for example. And the last one I also implemented was a symbolic strategy. What I did was that I basically lifted up the kernel implementation of red-black trees to a user space implementation. So I can easily use symbolic execution tools like CLI. And with that, I also had to give CLI some kind of limit. Otherwise, it will search for infinitely many test cases. So if you're really interested why I had to do this, there's also a section in my thesis. But yeah, in the end, we could also use symbolic execution to generate test cases and then apply them on the verified implementation and on the kernel one. So I've also collected then coverage information. So these are line coverage, and they are collected with gcov and not kcov. The reason for this is that the red-black trees are blacklisted in the kernel for kcov because we cannot be sure if we somehow hit a line in a red-black tree, in the red-black tree file, if this is really correlated with, for example, the insert operation that I previously called using a write system call. Because in between this write system call and the actual function that is executed in the module, some other red-black tree operations could happen in the kernel. I've divided this table into 2 coverage parts. So the core part is really what I've told or explained previously. It's the core part of the red-black tree algorithm without these auxiliary functions like RB next, RB first. An interesting thing that you might notice is that for the random strategy, we tested far less operations than with the exhaustive one, but the exhaustive one was much faster than the random one. And the reason for this is that the random trees can get quite large in comparison to the exhaustive ones. So yeah, I think we can move on to questions and discussions. Would you like to introduce the discussions, Lucas?
Sure. So I think what you've seen here is the first experiment in combining testing and verification around the kernel data structure. And we hit a number of, I think, technical problems, but also problems on how to continue this work. I think we'd be interested in some feedback. So as Mete pointed out, we have that, of course, the source code and everything on GitHub, but can we actually make such test Oracle setups accepted by the kernel community? So I think there are a number of questions how we can actually get such a thing upstream, as well as some technical questions on, okay, how do you actually use kcov when you only want to look at a subpart? And is there more interesting aspects in diving deeper into symbolic execution? Yeah, so we're happy to get feedback on those points. With that, I think, yeah. Yes, it's up to the audience. Let us know. Okay, because there's nobody commenting. And I guess the question is really...
Well, Daniel asked a question in the chat. can you talk some more about symbolic execution in the kernel context? So basically, I cheated on this part, right? I did not symbolically execute kernel code, but I lifted the required kernel code into user space and tested it then in user space. And this was easy because a red-black tree is really not dependent on many parts of the kernel. So I just throw out the RCU part and like the memory barriers, and then it just worked. But there exists one tool that claims to allow symbolic execution in kernel contexts. It's called S2E. It's a research project by, I think, EPFL, but I didn't use it in my thesis. It was quite complex to use, so I just used, because I also needed coverage information, so I just used the lifted up version for that. But indeed, that's, for example, something one could investigate even more when we would like to have, like what we said in the third point, a symbolic execution kernel pipeline in combination with oracles. You're welcome, Daniel.
Hello, we have a few minutes left. I just have a question. Do you think this could be run as KUnit or K-self-test?
So
I
I
don't know
think
if
it can,
K-self-test would be more for like runtime on a real machine, and KUnit, well, it's running in user mode Linux, but it could be run in more hardware abstracted way. Do you think it could fit in?
Yeah, I think
these
it can be
frameworks?
run. It can be run in both, as well as in KUnit as well as K-self-test. I think K-self-test is the more. I think K-self-test is the better choice here because we need to run the verified oracle next to it, and that's needing some interaction with the Haskell compiled program, right? So you need a Haskell interpreter that's running side by side. And I think that's also one of the questions for getting it upstream. We would want to drop generated source code in the Haskell programming language into the kernel repository. I mean, it's only in testing subdirectory, so I don't think too many people are going to look at it. But of course, we're introducing a number of new tools that you would need to run such a test case. Again, it's a much more complex setup than just a unit test. Yeah, and I think that's basically just the decision of the community.
So Lucas,
yeah,
this is Shua. K-self-test. We looked at the generated code aspect before in one of our kernel summits, maintainer summits a couple of years ago, related to Syzbot, because Syzbot also has several, Syzscholar and Syzbot have several generated cases. So what we have determined is we do not want generated code in the kernel tree, and it has to be a separate GitHub. Is that a possibility for you to keep that separately and have people, when they are testing the combination, pull that and use it?
That would be possible, but I think so what we're doing at the moment is we're generating the test, the verified test program once, and it's generated from kind of a formal specification. That's a bit different than the Linux arts repository you're referring to.
Right.
Because you're generating them in huge amount of cases, right? Here we're talking about one generated program, and it's going to be in Haskell programming language. So I don't think too many people want to just touch that anyway. If it breaks, then you need to understand how the whole generation works, how the proof behind it works, because you can't just modify the generated program. Then you basically don't know if you're testing against the verified variant. Right? So there are a number of implications of that. But yeah.
Right. So for all of these things, I guess make a proposal and send patches in, right? That's how you get the best input from everybody. I mean, we have generated headers, but it's and we have limited fashion, like Martin is pointing out, firmwares. But this is all we'll have to kind of look at what it is and what are the implications. So it is related to K-self-test, of course, and K-self-test, I agree with you that K-self-test is the best choice probably in terms of hooking the interface, arbitrary interface into it. However, we have to look at what it is that we are.
Yes. So I think we'll probably do that, and then we'll see how much maintenance burden and that really brings, and how long we can actually support maintaining that. And if it turns out in a year that this is just a pain, then yeah, we kick it out again. I think that's fine. But yeah, let's see.
Thank you.
Yeah, thanks.
Okay, thank you very much. That's the end of the allocated time for this talk, as we have a 15-minute break now, and there's also a poll. You can answer when you're back from the break, so we have an idea if everybody is back. Okay, thank you very much. I'll see you all in 15 minutes. Hello Dan, I've found your slides and I've uploaded it in Big Blue Button. So whenever you're ready, we can start presenting it.
All right, thank you. I think we've got like 7 minutes though till the end of break.
Yeah, six minutes, yeah.
6. All right. So I don't see my slides.
Okay, yeah, we can load your slides now if you want. That's right. Use match developments here. Then yeah, I'll wait for the end of the break and then I'll give you I'll make you presenter so then you can switch slides.
All right, thanks.
There seems to be some feedback. So if you're not talking, it's good to mute your mic.
Okay.
Thanks. There's 1 minute left, and apparently 22% of people are back from the break, according to the poll. Anyway, we'll wait until 10 past. Okay, so that's so yeah, I don't know why really, just to check whether people stay on break longer than the expected duration. Anyway, so now we're back with Dan talking about Smatch. So I'll make you presenter, and then it's over to you. Okay.
All right, thank you. My name is Stan Carpenter. Thank you for coming. I work for Oracle, and I'm the author of Smatch, which is a static analysis tool. I've got kind of two micro talks, and then a micro discussion, hopefully, in this presentation. What I want to talk about is the new param key API. So some of you have seen this slide before, and if you have, don't panic. In the past, I've given introductory or beginner talks. This is going to be an advanced talk for an advanced audience. So this is how we handle like a k-free in olden days. We'd set up a call for the k-free function, then we get the argument out of it, then we say that the argument was free. With the param key API, what I've done is I've extended how the data is stored in the database, and slides move slowly. I've extended it and improved it, and so now instead of asking for the k-free function, you ask for the argument itself. So you say the function is k-free, you want the 0 param, and the key is a $sign. That's like a wild card because, of course, the pointer is going to be called different things depending on the caller. A more complicated one would be release resource. And here's the key is $sign start. And that would be difficult to handle in the old code. But now it's quite easy to handle. So the match free function would look like this. It takes a long time for it to switch, and it's disconcerting. The match free function is just a one-line function. I don't know if you can see it. It's not that interesting. It's just one line. There you go. Wow. The beauty of this is that you can use the same match-free function for both the database information and the hard-coded information. I'm going without slides. It just looks like blank here. I wonder.
I can see
it seems to be working fine.
It's working for you? I'll just go blind. I'll trust that it says the right things.
Do you want us to switch the slides for you, and you just tell us when you switch?
It looks like it's going faster in this view.
Oh, okay.
So what you end up doing is you have one alloc function. Like this is from my check unwind script, which is looking for leaks. So in that module, then you've got one alloc function and one free function. But at the top of the function, then you've got a giant table which describes everything that's allocated, how it's allocated, and how it's free. So the IDA alloc range, what allocs is the return value. So that parameter is -1. And if it returns a 0 to int max, that means it's successful, and it needs to be freed on error. That's the end. All right. I think I would. Could somebody switch the slides for me? Actually, that would be better. Maybe. I don't know if that would work.
Yeah, sure. So right now you're on slide 7. It says and Michael talk one.
Yeah, good. Fantastic. All right. So the param key API just makes things a lot easier. And I end up, of course, it's so useful to be able to describe parameters. Easy is transformative. Yeah. So next I want to talk about, let's switch slides. And then next I want to talk about sleeping in atomic functions. So how this looks like in the kernel is when you have a spin lock, you're not allowed to allocate things with GFP kernel. But underneath, there's a counter, which is called the preempt count. And when the preempt count is non-zero, that means you're not allowed to sleep. So let me switch slides. It still is very slow. I don't know how to make it work. It was working for all the other talks.
Slide 9.
So, yeah, thanks. So I tried this, failed attempts for years, and or incomplete attempts and failed attempts. And I had a slide here explaining the stuff I tried, but I had to cut it out because I could talk. So this, you can't really understand how beautiful and this is until you've struggled with it for months and months. So at one point it was saying, of course, print K doesn't affect atomic at all or preempt at all, but it was saying, oh yeah, that decrements the preempt count 7,000 times. And so it was just garbage. Because of version and because of I think place which we draw a lot of logs. But how you can fix that is with check preempt info. And of course, this one's got another giant table. I didn't really probably need that, but I had the functions already, and so I just copied and pasted them. But the beauty of it is it doesn't track the current preempt count. It only tracks if you increment the preempt count, which means you take a spin lock, then it sets the state to increment. If you decrement it again, it doesn't say back to decrement, it says to ignore. So if you increment it twice, again, that's an ignore. And then it records that information in the return states. So what we're recording is that this function on this return path increments preempt count once, exactly once. And it's not like the whole function. So like spin try lock, if it succeeds, it doesn't modify preempt count, but if it fails, if it succeeds, it does modify it, but if it fails, it doesn't. Let's go to the next slide. So then you got, could we go to the next slide? So then there's a check preempt, which does track all the current status. And it uses the information from check preempt info. It has like a callback, so every time you increment or decrement, it's recorded in check preempt. And it stores that information in the caller database for caller information, if this function is called with the spin lock help. And it reads that information about how the function is called. It also exports get preempt count, so we can use that later. And sometimes functions are called, sometimes with preempt disabled and sometimes with an enabled. And so there's an atomic check, which if it's true, preempt is incremented. Next slide. So maybe I'll just take over the slides again if I could. It doesn't make any difference. So then the other part of this is the check sleep info. check sleep info, looks for GFP kernel, and it has a list of functions to sleep. It's a little bit complicated, more than I've written here. Is it? Maybe it's not. It's that simple. Let's say it's that simple. And it records in the database if this function always sleeps. Then the check sleeping in atomic, what that does is just one function, and it hooks from sleep info. If there's a sleep, then the callback's triggered, and it looks at the preamp count is greater than 0, and it prints a warning. It's just one function. It's very easy. And then the other critical part of this, which makes it all usable, is the change to smdb.py. So if I have a warning as this example, then I can check how it's called with preempt. So this is exactly what the smdb.py script outputs as unmodified. So it's very clear tree. So I have a script to highlight it, everything, and then I just go look at the call quickly, and I can send that in their bug report, and that's it. And it unfortunately, right before the talk, I realized that I think the real-time stuff has messed up the this module. It's a little bit of tweaking, but it's simple enough to solve. And I really like the increment, decrement, ignore one. I'm tempted to rewrite my locking check to use that, and reference counting could be done. The other thing is that there's a lot of good stuff in the database. I feel like the database is undervalued, but it's so useful. And I also like how much it's split up. The original code, this was one file, but when it's 4 files, it's easy to debug, easy to handle. So that's it. That's the end of that part. I don't know if you're applauding, but it's like it's honor system. The next thing I want to talk about is race conditions, and race conditions have been frustrating. If you look at Syzbot, and we're all looking at Syzbot and Syscaller, and race conditions are a huge cause of bugs, and it's hard to fix them through static analysis. And if a static analysis can't fix it, it's hard for even humans to fix it. So if you look at Alexander Paul sent this patch, it's slightly modified, but it reads from SK transfer, and then it locks the socket, and then it uses it, which it should be the other way around. And the lock sock actually makes it worse, because if you just didn't lock it at all, the race condition would be unpredictable. But with this, you set up contention, you free the SK transport, and then you release this lock sock, and it's a use after free. So that makes it easier to analyze as well from static analysis. Here's it's free. This transport destruct frees the transport, but it actually doesn't free it directly. It puts it on another list, and then a K thread worker thread frees it. So Smatch doesn't flag next use after free, because you'd have to hit a race condition before that would be a use after free. So there's all kinds of race conditions, and some of them are never going to be triggered. And it's hard to know what to do. So anyway, so I looked exactly Alexander's bug. And I got 8 places where we should have called lock sock. 2 of them were bugs, and 6 of them were false positives. And one false positive looks like this. We check here, we're dereferencing this. We shouldn't be dereferencing this. but actually we check it again inside the log. So that's fine. It's just a shortcut here, but it's hard to debug that. You know, you want to print the warning here from static analysis. I guess we could silence that, but it's difficult. It's all tricky. Lucas and Julia, I think, I don't know. They're both smart people. They probably both told me this, is that we could infer the locks, which locks are needed. Instead of saying instead of just hard coding in that this needs to be lock by lock sock, we could infer it because it's the next line. And so once you infer that lock, then you get a lot more warnings. You get like 600 warnings. And I haven't gone through them all. There's a lot of false positives. Inferring locks is not 100%. And it's very hard to analyze. And I was also looking at which ones were going to cause problems in real life. And that's tricky as well. I'm not sure people would welcome patches. It's tricky because I don't like to send patches which could break the code. I like to know that, oh, this code is gonna crash, right? So, and nobody wants to get 600 static ticker warnings and go through them. Even I don't want to do that. Norbert, Sarah, this fix. And what it is there's a missing lock sock. And I mentioned before that that code would have been hard to exploit if there weren't any lock sock. But this code, what makes it editable is this copy from socket. So when you're copying from user, there's ways to delay that so they get a slight hang. And then you win the race conditions. You organize the race conditions to work out the way you want. So what this code is doing, it says, if we've already bound the socket, then we can't change any settings. But because of the race condition, we start to change the settings, we hang the process here, then we connect, and then we change the settings, and then boom, crash. And I believe all these bugs were from syscaller. So we're all looking at syscaller and trying to figure out if the bugs can be prevented with static analysis or exploited or whatever. And of course, both of these and Alexander are fixing bugs, and they're very clever people. So yeah, copy from user, you can make it hang there. So let's look for that bug again. And here's one which is exactly the same bug. You got port count. If it's open, you're not allowed to change the settings. Fortunately, in this case, you're only allowed to change the settings if you're already basically root. So, so that's fine. It's not fine, but it's hard to exploit. It's not an exploit. Then that's the end. No, life lessons, of course. Norbert and Alexander might be able to go through the 600 warnings and figure out if some of them are real bugs and exploitable bugs, and they might have fun doing that. But no maintainers want to deal with that. So in some ways, static analysis is better, more useful in this case for attackers than for maintainers. And my other thing is that locking is just so complicated, and there's always exceptions, and we're like, oh yeah, in this case, you might be right, but you're not wrong. You're not right because we haven't exported that or whatever. Maybe annotations would help. In Smatch, I basically don't use any annotations. There's one check which uses user annotations. I love user annotations. The locking annotations, I kind of hate them. They're kind of rubbish and unnecessary. What I would want from annotations is maybe something human readable, and I could run a Perl script and get information and create my table from it. And then the other idea that I had is that maybe somebody could inject a little delay into every lock or every unlock or every copy from user and run syscaller with that. That was my ideas. So are there any questions? Is there anybody there? So the chat matrix is also not working for me.
There's no questions so far on the chat. There's 5 minutes left.
I was hoping somebody would have some ideas on locking. It's so complicated, and I wish people had ideas on how to formalize things so that we could analyze it in a static checker way.
There's a discussion about Rust a bit later, so that's not an answer.
I just wanted to say thanks for at least looking into it and experimenting with it, because that's super complex, as you said, and it's just like writing assembly code. It's at some point you're going to have to write some, and it's the same with locks, but it's not. Unfortunately, we need to write locks more often than assembly nowadays.
Oh, thank you.
Have you thought about an annotation on the data? Like if you touch this data, you must hold a lock that goes along with it.
I feel like in a struct, I kind of prefer like a multi-member way of annotating. So you could annotate like 4 members in a row instead of adding on like a thing on the end of each. But that would be nice, yes. I think that kind of thing might help human readers as well.
I think it helps everyone.
Yeah, the locks, when you create a new spin lock, when you declare a spin lock, you have to add a comment, otherwise checkpatch will complain. But those comments are not very useful, I don't think. They're probably better than nothing, but I haven't ever found like that's super useful.
So are you looking to key all of those comments to be able to check for lock semantics?
I mean, of course, I'd love to. Yeah, I'd love to be able to do that.
Would it help if the comment said which fields in the struct it protects?
Yeah, if it were something that was in a like kernel doc format or something like that, yeah, if you could parse that, absolutely. So the other thing is, I don't know if I printed the actual warnings. Yeah, there you go. I probably should only look at the this last thing, but like for lock sock, it's a much more complicated thing, and it is sometimes renamed different depending on how it's called or something like that. So you run into that thing where you assign a lock pointer to something else, and so it comes up that it's a different name, but it's the same lock. Yeah, that's a problem generally in Smatch. It doesn't like when locks change names, where yeah.
I've been toying with, outside of the static analysis, I've been toying with marking members or like data that needs to be locked in some way that I could then trigger case and accesses on it to kind of stop and then check that the lock is taken when it's accessed, like even for read. So I've been trying to think of a way to kind of annotate data that needs to be locked and which lock needs to be held when those are accessed. I think it's beneficial for both those static checkers as well as runtime stuff.
Yes, absolutely. And of course, the example that people are going to give you, the counterexample, is that in probe functions, or when the data is not exported, then there's no need to lock it. But I would just always lock. Probe functions aren't fast path. So
right, and I would argue
there's no contention.
Right, and I would argue that it's fine just annotate the exceptions. If you don't want it locked, just find a way to kind of explicitly annotate that I know it's not locked here on purpose. You know.
Sure. Yeah, I think people would just lock it in the probe functions. Yeah. There's no contention. It's easier to lock it than to annotate it. And so that'd be good. Yeah, I'd love that.
I'll try and get something just so we can start talking about it. I'll send like an RFC.
Fantastic.
Okay, thank you very much, Dan. And now it's time for the next talk about fuzzing device interfaces with protected virtual machines with Felicitas.
Yeah.
Are you ready?
Yes. I hope you can hear me well.
I'll make you presenter. Yeah, okay.
Okay, thank you. Yeah, hello. So my name is Felicitas Hetzel. I'm a PhD candidate at TU Berlin. And my colleagues and me, we have been fuzzing the device interfaces of protected virtual machines. And the reason we started this project is that there are now a lot of technologies released, or at least proposed, namely AMD SEV and Intel TDX, that aim to protect complete commodity operating systems, including all the device drivers from a potentially malicious hypervisor. And I don't want to go into specifics of how this is achieved, just suffice it to say that with these technologies, the hypervisor, including all the virtual device implementations, is excluded from the trusted computing base. And there have been some efforts to create a secure virtual device interface. So for example, TDX has proposed an implementation for device whitelists so that only specific devices can be attached to a protected guest. And in addition, you have the SVIO TLB component that is used to bounce memory in between protected guest memory and unprotected or unencrypted memory that the devices can access. So now with these technologies, you have a trust boundary between the virtual hardware and the operating system. And this is sort of an issue because virtual devices, or like hardware devices in general, mainly used to be trusted under the Linux threat model. So there is insufficient sanitation on data that is received from devices. And also we found that oftentimes you will have secret or control data like kernel pointers that are shared or even under control of the device. And another thing that we noticed is that sometimes if the driver fails to initialize part of its state due to values reported by the device, these failures will not be probably recognized and handled, leading to the driver code later accessing these structures. Yeah, so we've been fuzzing this interface, and it's actually kind of tricky due to several reasons. So for one, you have a lot of embedded delays in the driver code. For example, a common pattern that you would find is that the driver will write a value to an MMIO register and then sleep for like a few microseconds to a second and then read back the response from the device. And obviously, this is pretty detrimental for your fuzzing throughput. Another thing is you have to think about how you actually want to inject your test cases into the I/O interface, because compared to, for example, the user space OS interface where you have system calls, it is at least parts of the I/O interface are not as easily accessible, I would say. Then there's IRQ scheduling. So I guess you're aware that most driver device interaction is triggered by IRQs. But another thing that happens a lot is that a driver would enter a blocked state in waiting on a resource that has to be provided on an interrupt path. So ideally, you want to recognize when this is the case and schedule interrupts in a timely manner. Then there is state accumulation. So you keep interacting with the driver you're analyzing and the kernel environment. And at some point, it might happen that you reach a state where you cannot productively continue fuzzing. So then you will have to reset your environment, and that costs time. We also had issues with a lot of shallow and non-exploitable, so non-interesting for us bugs. And specifically, there was a lot of bug error handling is what I called it here. So if the device returns an unexpected value, the kernel would just panic. And then again, you have to reset your kernel environment, and this will again cost you fuzzing time. And lastly, there's an issue with coverage stability. So coverage stability means that if you execute the same test case twice, you ideally want to trigger the same code paths. But in Linux, you have like a lot of concurrent threads. And depending on the order in which they are scheduled, different threads might consume different parts of your test case and produce a different coverage signal. And your mutation algorithm is, well, it's really suboptimal for your mutation algorithms if that happens. So now the reason these points are grouped into 3 sets is that we were somehow able to solve or address the first 3. State accumulation we managed to somehow alleviate, but it's still a little bit of a problem. And the last 2 points are things that we still have to think about. Yeah. So we built a tool to analyze this interface. It's a targeted driver fuzzing tool that is based on the Linux kernel library, LKL, and libfuzzer. And LKL provides the drivers and the kernel environment, and libfuzzer provides the mutation and test case scheduling. And so this is an in-process user space fuzzer. And the whole framework consists of several components. For one, you have the target driver that you want to analyze. This is compiled from the LKL source code and loaded as a shared library. So it's compiled as a shared library and loaded into your harness. Then we so far implemented 3 device stubs, namely word.io, PCI, and platform. And each of these stubs can be used to analyze arbitrary device drivers of the corresponding type. Then you have configuration files. These, for one, specify the driver you want to analyze, and also the specific device configuration, like, for example, MMIO resources that are required by the driver, and device identifiers. For example, for PCI, you would have the product and vendor IDs in those configuration files. And then lastly, for libfuzzer in general, you always have to write a little harness that invokes interesting functions in like the library you want to fuzz. And similar here, we also use a harness to trigger interesting functionality in the analyzed driver. So for example, what the harness should do is to initialize and uninitialize the driver and to trigger interrupts, and further you can call arbitrary system calls to either like exercise interesting code paths in your driver or configure your driver. For example, you could set an MTU value for network device drivers. We solved I/O interception in two ways. For streaming DMA, MMIO, and PIO, we just adapted existing kernel interface functions to just consume and return or inject data from your current test case. And unfortunately, for coherent DMA, you don't really have any convenient interface function that you could adjust, because ideally you want to return new values on each access to a coherent DMA memory area. So what we did instead is we piggybacked on the address sanitizer instrumentation. So I assume you are somewhat familiar with address sanitizer, but basically you have this shadow memory. And what we did is we marked the shadow memory that corresponds to coherent DMA allocations with a special value. And we adjusted the error handling code of ASIN to, instead of throwing an error, to inject data from our test case into the coherent DMA access and then continue execution. To address the delay issue, we just removed delays in driver code. So we have a compiler flag that is set when compiling the target drivers. And what this does is it replaces the functions that are commonly used to implement those delays with our own version of those functions. And our versions basically just either reduce the delay to a very small value or return immediately. For IAQ scheduling, we track whenever item is added to one of the Linux wait queues. And if this happens, there is a thread running in the harness that is notified and triggers an interrupt immediately. And to alleviate the state accumulation, we just load and unload the driver in each fuzzing iteration. Obviously, this would just reset the state in your driver. So there might still be state accumulating in the rest of the kernel environment, which might theoretically lead to problems, though we didn't encounter any so far. So with this tool, we get around 570 executions per second on average. Obviously, this really depends for one, like on the hardware you're using, but mainly also on the driver you're analyzing and the complexity of your harness. The paper, yeah, I wanted to provide you a link to the paper. Unfortunately, it's still pending in the archive submission process, but I will probably add it to the source code repository that's also linked here as soon as this is through. Yeah, so this was the current state. We've been thinking about how to continue from here. So one thing that we've been discussing is to actually move this whole setup into a proper VM setup. So all the adaptations to the Linux kernel library that I just mentioned should be pretty easily transferable to like a normal kernel. The only thing I guess you would have to work on is to enable kcov to actually trace coverage for all the kernel threads that consume device data, because I think currently it's only able to like trace coverage for system call paths and some USB workloads. But a main advantage of having this in a VM would be that you can reuse all the existing virtual device implementations that come with QEMU. And what would that would allow you to like either just modulate valid communication, or even instead of fuzzing like all interactions between the device and the driver, to just pick a single, for example, DMA buffer and just fuzz that. And I guess that would probably improve coverage or like allow you to reach deeper code paths within your driver. Yeah, AKL unfortunately does not support SMP or preemption. So what you cannot do is just trigger an interrupt at arbitrary times. So obviously this greatly limits the capabilities of our framework to find race conditions. And lastly, the way LKL is implemented is that you have your own LKL architecture under arch/LKL. So any code under arch/x86 is not part of our framework and cannot be analyzed. Though I'm not sure if there's anything interesting there to analyze because the BIOS is actually also measured. So there is no trust boundary between the BIOS and the operating system. But yeah, I would have to look into that. There are also some advantages to keeping this in user space. So for one, you have all the nice libfuzzer features. We've already been experimenting with data flow tracing, but like in general, there are more tools for program analysis available in user space. So for example, it would be interesting to do some experiments with symbolic execution. And lastly, I guess the overhead is a bit less, meaning as well like the setup overhead and the usability, but also the runtime overhead. And besides the interfaces that I've just mentioned, there are other interesting interfaces that would be worth looking at. So for one, there is the interface between the hypervisor and the BIOS. There's the QEMU firmware configuration interface, and there are also like special emulated instruction, for example, CPU ID. I've also been working on an interface layer to reuse QEMU virtual device code in LKL. I only have like a little anecdotal data, so I've already ported the XHCI host controller device from QEMU to LKL, and you can actually copy most of the code. You just have to replace the QEMU interface functions with the corresponding LKL interface functions. But I guess this could be abstracted away in an interface layer. And lastly, we've also written a static analysis tool for this interface. It was based on Smatch. So what we did is in Smatch, there's actually already a checker that traces user space data through the kernel. So we based our checker on that and replaced the functions that identify user space data with the functions that either return device data or map or allocate DMA memory areas. And then we just check what happens with this data. So you would get reports if such data is used in pointer arithmetic or if any kernel pointers are placed in DMA memory areas. And well, unfortunately for us, but fortunately for this community, I guess we had to stop working on this because another group actually published a really nice paper that does something very similar to what I just explained, but they go beyond. So they actually add, I think, lightweight symbolic execution on top to reduce false positives and also make the analysis more sound. So I would also encourage you to look into this if you're interested. The link is provided at the bottom of the slide. And that basically concludes my talk. But I have like a lot of backup slides. So if you're interested in the parts of the framework or the bugs, just I'm prepared to answer those questions, I think. Okay, thank you.
There's a question in the chat if you want
Yes.
to maybe start.
Is it 170 executions on a single thread test process or per machine with multiple test processes? No, this is, it's one core. Does that answer the question? Okay, yeah.
So how do you measure coverage, which are like how much of this, like for the drivers which you're analyzing, like how much of the code paths which interact with this different, taken input for these different interfaces have been actually reached?
Yeah, so we use the standard Klein compiler options that are recommended for libfuzzer, and we use this coverage, the reported code coverage by Klein. And we only instrument the drivers that we're analyzing.
So what kind of coverage have you been able to reach for these drivers?
I
mean, roughly.
Yeah, actually, let me look it up. I think it was between like 5 and 25% of code.
But this is between 5 and 25. This is a generic coverage for all the code paths, right? It's not the bounded to the actual paths which are going to take this MMIO input or something. Or did I misunderstand you?
Yeah, this is for all the code paths that have been traversed in the driver. Obviously, there will be some parts of the code that are traversed due to system calls issued in the harness, and some parts that will be traversed due to interaction with the device interface.
Okay, so you don't filter like so you don't try to get to coverage, because I'm trying to explain because we are doing very similar, and what we're trying to because there are many ways how you can fuzz all of this, and we're trying to basically assemble the coverage of all the paths which, let's say there are 1,000 paths which will lead to different MMIO rights for our analyzed surface, and we're trying to collect the data how much our fuzzers can reach these particular paths. So we're not just generally interested, how much a fuzzer can trigger different paths in this particular driver, but we're only interested, can it actually reach that, number 100 or so which are present and which we know will take a different, MMIO input or PortIO input.
I'm not sure. I'm sorry, I'm not sure I understand the question. So could you maybe rephrase it?
So what I'm trying to say is that so maybe I'm not using the right terms. I'm not myself a fuzzing person. So, but we when we analyze this, because I said we're doing very similar project basically. So at Intel, so we are looking also at, let's say, PortIO, and if we focus on PortIO and MMIO. So, and we know that in the kernel, even if we drop, we don't have to look at most of the drivers. We already mentioned it, we whitelist only a small set. But if we take this whole set of a kernel plus with drivers, we have a static analytic pattern actually smudge as well, but it's worked differently. It produces us a list of all the places where MMIO happens, let's say, and PortIO happens. And we want to make sure that our fuzzer reaches all of these places, and particularly certain ones, because we even flag them as being most likely to have problems, because we look at this also do manual audit. So this is what, for us, this is the meaning of coverage. So we want to make sure that our fuzzers, we use actually a different type of fuzzing, but they actually reach these places. Because otherwise it's very hard to say, well, yeah, we have 25% of code coverage, but have we actually, how much of these useful places for us we've reached?
Yeah, it's actually a really good point. I should probably have evaluated that. Unfortunately, I just have what libfuzzer gives me as code coverage for now.
And maybe another question, because again, as I said, it's very similar issues we are looking into. We have had one problem with the stimulus. So because our fuzzer is also injection points are quite passive, so we need to find a good stimulus to execute this code. And maybe not so much in drivers, but also in the core code. So have you researched what can be a good stimulus for this kind of low-level code? I mean,
you mean how to make the driver actually access the device interfaces?
Yeah, so perform this MMIO, PortIO, and so on. So of course, the initialization step is very useful, because there's PCI config space and all these things can happen. But when in a runtime, I mean, it's actually we have found this being pretty difficult. So to actually to get a good coverage in terms of what I explained, but try and find a good stimulus. So maybe it's obvious for some drivers, but it doesn't seem to be obvious for all the code we're seeing.
And also most things have more initialization. That's not a problem yet.
I'm sorry, I didn't acoustically.
Andrew, you're feeling very far from microphone.
Okay. So is that most things, at least in the core, happen only at initialization. So you have to reboot or reinitialize all the time. And I think the same is true for drivers, that a lot of stuff, like for example in Word.io, it has this complication negotiation step, but it only happens once at the beginning. So you would need to re-execute the beginning all the time to fuzz it.
Yes, I mean, that's kind of what we do. We initialize the driver in each fuzzing iteration.
Okay.
Yeah, okay. There are a few more questions in the chat. Let me see. How much of this is specific to fuzzing, or is it applicable to any drivers? I mean, if you so a thing that's maybe not as applicable to virtual machines is like fuzzing USB drivers, which we started looking into. And all of these optimizations should also apply to the USB target, I think, for fuzzing from the user space side. I guess I don't know how much sense using our framework would make in comparison to just using syscaller, especially since syscaller has a few nice features like triaging coverage and stuff like that that we don't have. This another. What are the high and low bugs on this slide? Oh yeah, so I briefly mentioned this. So a lot of the bugs we found are actually not exploitable. So for example, invalid access or just reachable assertions. So the high bugs are the bugs that have a chance of being exploitable, and the low bugs, in our estimate at least, are not exploitable. Yes. A question about this slide is difference between VRD and ND. So this actually evaluates the improvement by removing delays, as I mentioned before. So VRD is fuzzing drivers with delays, and ND is fuzzing drivers without delays. Number of blocks is the block coverage reported by libfuzzer. And TTV on, I'm sorry, maybe I should have included this in the talk. This is just an overview of how much time it took the fuzzer to find the first bug in each of the drivers. Yeah. Did I miss anything? Okay. Yeah, I would actually be interested in the Intel's approach to this. Is there any anything published yet to look at?
So there is a talk. It doesn't go into deep into the fuzzing. It does show on high level all the fuzzing setups we have so far. There's a talk on Linux Security Summit next week on hardening with Linux. I don't know, I'm trying to remember how it was titled. Yeah, but I think we can also talk directly. So using basically different fuzzers, KFX, KFL, and we have different setup based on it. So.
Okay, yeah.
And actually we're having a match button, but it works a bit differently. So it looks like there's a lot of similarity here.
Yeah, looks like it.
We have 2 minutes left in case someone else has any more questions.
Yeah, hi. So I wonder how difficult it would be to port the fuzzer over to be able to run against a Linux kernel image. It could be a special Linux kernel image enabled by which just takes some or which needs to have some config enabled, which is just for debugging or something. But would that be feasible?
So you mean instead of using LKL, using normal Linux kernel source code?
Right. Yes.
I think it would be. I think I briefly talked about this. So I guess except for kcoff, it should be very easy to transfer the changes to like a normal source, normal kernel source.
Okay. Yeah, that would be great, because then we could run it continuously, right, on your kernel versions, and that simplifies integrating things into a CI and.
Yeah, exactly.
Yeah, so this is basically was one of the requirements we had. So we wanted something which doesn't require like much of a manual instrumentation. I mean, because it's with this fine tuning and stuff, it's great to find bugs faster, but it doesn't scale well for her kernel. Like if you think of non-driver code, like architectural code and so on. So they wanted to set up which would be like independent of all of it. So you can just, like you said, you take a kernel, and you can kind of, you put a couple of patches on top of a guest kernel and top of patches in the host kernel, and like install a fuzzing framework, and you can just keep switching your guest and basically continuous fuzz. So they have been trying to work on that direction. So.
Yeah. There's one more question. Do I have time, or let's skip it?
Sorry, now this is time to carry on with the next topic, but I guess you could continue discussing maybe on the chat or in a hacking room.
Okay.
Because we're really tight with the schedule, so if we start diverging, we'll have some issues. But thank you for your talk; that was really interesting. Next, we have Miguel talking about testing in kernel Rust code. Miguel, I've made you a presenter. Is that working for you? Okay.
I was working with the camera because I switched rooms.
Okay.
And I have to enable it. Okay. Okay. So let's start. So yeah, this is one more Rust talk in the conference. Thank you for having us, even if we are like a bit spamming LPC with Rust talks, but since well, adding a new language is a bit of or touches a bit on many subjects. I think one interesting subject was testing how we are going to do testing for Rust code. So first of all, what I want to do is give you a quick overview for those of you that perhaps don't know or have not used Rust so far. In fact, actually, we can make a call. Paul, if you don't mind. Sorry, true, false. I don't know if you can see the poll. No, it doesn't seem to work.
I think it's visible. The presenter doesn't see the poll, only sees the results, but everybody else can see the true and false, like, in principle.
But I don't see any response, so okay. No, hi, it's not working.
I just responded.
Okay. The other day this was fine. Okay, never mind. Okay, it was just wanted to see how many of you had some experience with this. Anyhow, so sorry, I cannot publish because it went away as well. So I don't know what happened there. Anyhow, so this to give you an example, let's talk first about the user space quickly, how it works testing in Rust in user space, so normal Rust code basically. So imagine that we have three functions, right? This function returns x+1 but has a bug, as you see here. This one panics when the number is negative. And this one uses a result, which if you don't know about, is a sum type, which basically tells you whether something is contains either an OK value or an error value. So either successful or failure. In this case, in the OK case, in the correct case, contains an integer, and in the other case, nothing, so empty. So it only has the knowledge of an integer and whether is successful or not. So we are going to use these three functions to show you how the code looks like. So for tests, in Rust, we will write this in user space. I will describe a bit how it works. Basically, this is a module. It's not needed, but this is idiomatic in Rust code to write a module for the tests if they are unit tests, not integration tests. But just doesn't matter the distinction right now. Then use super. Basically, this imports everything that is, for example, in the top of the file, because this can be in the same file. So the previous slide where the functions were, imagine that it's a library or it's some code and you want to test that very thing, you can put it in the same file, and then you will import this into this namespace so that we don't have to repeat here, or we don't have to put a namespace here. And then you list some functions that you annotate this in an attribute, and we annotate them as test. And this means that automatically they will be picked up by the testing system, and it will be executed one by one. And then there is some macros and some facilities for the usual stuff in a library, in a testing library, as you know, assertions for different things. This, as we will see, is two parameters, so that, as you know, it shows in the output the two parameters, the evaluation of both of them, so you can see the comparison, etc., etc. And then we have here also this, which is conditional completion in Rust, and this is used so that this code is not compiled when you are using the test mode, basically to compile the tests. So if you are in a normal build, you skip completely the entire module. So this is basically how it's usually written, but it's not required to do like this. So anyhow, this is how tests, normal test, one does assist, one does fail looks like. And quickly, well, yes, there is, we can write it in the same file, or we can also put it in another file. If it is in another file, in normal cargo projects, user space projects, what they do is have a test folder where they put the tests. And those are supposed to be the integration tests, so they don't have access to the private function, for example, of a particular file, if you want to call it like that. And the other ones, the ones that you write in the same file, would have access to the private functions. There is some discipline. Some people say private functions should be tested. Others say they shouldn't. But anyhow, both things are supported. Then we have also support for Rust support. As you know, Rust code can panic, which means basically an abort for the kernel list. It's basically an abort. In the kernel, it will be like a kernel panic or a similar facility. We can panic in a test, which means it fails. But we can also say, or again with an attribute, we can say this test should panic. So there is support to test things that should panic as well, like the death tests if you want in other libraries. Then we also have the ability to ignore some code, some tests. And ignoring is useful because sometimes you have code that you don't want to test all the time, but sometimes you do. And then in the cargo command line, you can enable things that you have to know. So you can have like a default set of tests to run, etc. We also have tests based on result that can return results. So instead of using the normal way of like with the asserts or panics to know whether it failed or not, we can also use return whether the test failed or not, just with the result. That is useful in order to be able to use this easily to use this question mark operator. If you don't know Rust, basically the question mark operator allows you, it's like an if, where you, if there is an early error, if it failed, then you bail out, propagating or bubbling up the error to the caller. So instead of having to write an if all the time, if the type match, etc., but the details don't matter, basically it is like an if, and then you can change this code. For example, you may call the function, you remember that we have that could fail, and return a result here with the question mark operator. This x will be the integer. So it's already, if we arrive here to the x, if the x is assigned, then we already know it is correct. And then we can call that again, or any other function, so you can change the calls that may fail easily to make a test. Then we have also benchmarks, but this is an unstable feature, and it's not too, I guess it's not too important in the beginning for the kernel. So if you run in user space, you see this kind of output. As you see nice colors, whether something was correct or failed, whether something was ignored, and there is a lot of options, some options that to tweak, to filter, test, etc., etc., etc. The usual thing in such a library. The good thing is that this is integrated into the library, and basically every project uses this. And I am explaining this because the question will be later: do we want this in the kernel? Somehow, and we will see. And then there is another feature that this is, I think, very, very important, and we actually use it. We use it. The standard library uses it as well. And in the kernel, we even caught a bug already, or a mistake, let's say, with this feature already. So there is you can write, for example, examples in the documentation, and these, if you know Markdown, this is a code block, and this example will be also tested. So when you run the cargo test that we saw, if it is user space, it will run this test. So it will actually check that this compiles and runs and does not panic. And if there is an assert, etc., it also checks that the values are the same, etc. There is also support in the code documentation. There is also support for ignoring. There is also support for tests that only need to compile. So they don't need to run. You just need to check that the syntax is correct. You can also check that the syntax is incorrect. I don't think that's very useful for us in the kernel, but that's fine. For some examples, it may be useful to be able to tell the user, don't do this, for example. And there is also, again, for functions that may panic, you have support for the same kind of attribute as we saw for the other tests. So for the documentation tests, we have the should panic attribute for the test, which means it will test that this panics, the same thing as before. So basically, more or less, the features are more or less the same for all the kinds of tests. And this thing that you see here, that I put it in order to also show you that, as we will see some screenshots later, this functionality is used for hiding this in the generated documentation that we will see. So this will not be shown. If you run the tests with these tests added, you will see also this in the command line. Again, this is all user space. So you will see this. You will see, for example, that you see both in the assert quality, you see both values, etc., etc. It's just a thing. The benchmarks also look like this, but again, this is an unstable feature. We could use in the kernel perhaps with some tweaks, but anyhow, I don't want to extend myself there too much. So how they do quickly, how they look like in the documentation. So in the documentation, this is, for example, how it looks. The crate I created for this example. We have the three functions here with the first line of the documentation here. And for example, for the one that may panic, we see here the documentation, we see the examples, and you remember the thing that we have, that we were hiding in the code. We don't see it here, so the documentation looks like this and doesn't need to have some details. We use this already in the kernel for some purposes, so it's useful. Also here, as we will see, in the left side, this is the other one with a bug, and we have four examples. This was one that needs to compile. This was one that was ignored. This was one that is not run, so it just compiles, and this is one that doesn't compile. And as you see, I mentioned this here, not because perhaps very useful for testing, but it's just an example that the documentation generator, if we use this kind of documentation, is aware of, for example, the tests and the text syntax, etc. So as you see here, they use it to mark this automatically. There is also in Rust Analyzer, which is a tool to, well, it's an LSP server, so a language, sorry, I forgot the S, language server protocol to, and let me move to the chat, sorry, so I see the chat in case there are questions. So Rust Analyzer is on one side is an LSP server for many, for example, Vim, Emacs, etc., for many editors, but also for Visual Studio Code. And in Visual Studio Code, they have some extra features. And for example, if we put if I show you how it looks like in Visual Studio Code, in this case, you see here, for example, this button. There is buttons that you can click to run tests, etc. This is very nice for user space, of course. If you are developing, it's very nice to just click and run all these tests, etc., etc. You see also here that there is syntax highlighting. Sorry, you see here that there is syntax highlighting for, as I was showing you before, in the editor. So the editors already recognize these things so that you can read the code without seeing the green or whatever color you have in your editor. The other tests would look like this. The normal unit test and integration tests would look like this, and also the editor allows you to run tests and debug, etc., etc. So these are all features of user space, right? Of course, it would be nice if we could have this button work in the kernel. We will see. But the point is in the kernel. I'm focusing now in the kernel. We have, this is code that we have right now in the kernel. We have a function that trims white space, trivial one, takes a slice basically and returns a slice. And we test it like this. We tested something like this. And this, we have this function. This is the easiest one that we test basically in the kernel right now. And I think it's quite nice to have this right near the, basically very near to the actual function that you wrote. And then for the other kinds of tests, we have, for example, here, as you see in the kernel code, we have in the kernel code we have some tests here. This test will give you the basically right now. We only test in the host. We do a hack to be able to run this code, the ones that we can, some of the ones that we can in the host. So right now, the support that we have for testing the kernel is only in the host. But I will, in the next slides, I will show you what we can do perhaps about it. And as you see here again, for this example, we hide this. We use that feature, and we hide this function test wrapper because right now, since we only can run this in the host, of course, we cannot run some code here. So basically, we use this as a way to only have like a compilation for this test. Let's say. I wanted to mention also that these documentation tests, even if it's only compilation, so checking for types, etc., it only compiles the thing. It already caught a mistake. So it's actually having the example. It's not just nice for user consumers of the documentation. It's also nice to have examples, etc., so it doesn't get out of sync. So I think all these features basically, and this is the end of all the features and how we use them. All these features already, I think they are useful, and it's something that is quite nice to use. This also is another example, as you see here. There is no code being run here. There is no code being run because this implementation of abstract. So this is not code that will be run in the test. So ideas for the kernel, what we want to do to expand on this. And this goes with, this basically is a discussion with, going into a discussion on key unit and self-test in the kernel. So one question is, of course, do we want to use key unit, or how would we use key unit and self-test with Rust code? We could write perhaps a module or something in C and then call the Rust side of the kernel, etc. But I think it would be perhaps nice, or it would be easier or more, since the language already supports this and the tools support this. Even if we don't use cargo, we don't use that cargo test, we don't use cargo, but still we can run the tests. And we can basically, we trigger the commands that cargo does in order to run these tests, etc. So we support the test as you saw. We pick the test and we can already identify the test and run them or compile them. So the idea would be perhaps to, if we want to do it in Rust again, to have another attribute or something that allows us to tell quickly. Here, I don't know if you can read it for me. I saw also in other presentations some of the letters were strange, but it's host basically, right? So we could mark some tests to be run in the host, like the trim white space. The trim white space function that we saw, that can be run anywhere. It doesn't even need to have a kernel running or anything like that. It could be similar to user mode Linux. Even not even that. We can just compile it as a Rust code, pure Rust code, user space. So this could be one type of test that would run very quickly or very easily. But we could also have user and kernel space tests. This would be in the target, so cross compilation, etc., would apply, and we would need to have somehow a way, for example, to either we, for example, do like key unit or self-test where we run them at boot or something like that, or we have a way to trigger them after a kernel is booted, for example, in QEMU or in an actual kernel running in a physical host. But we could perhaps also have a way automatically to spawn QEMU, etc., and run things. I don't know. There are several ways we could do this. We could perhaps reuse some part of QUnit or all self-test and map basically this. Use the compiler, those compiler to map this into or generate automatically a QUnit file or a self-test file, and then you reuse the framework there. But there are several ways to do this. Basically, my question is whether you would think this is useful. It could be useful. Of course, this is simplified. We may need more things here. We may need, it may depend on, again, on configuration, on conditional compilation, etc., on key config, etc. But the idea is to have different kind of tests and use Rust, the Rust way, so to speak, of writing tests very easily in the Rust side. And similarly, we could even think, again, for the doc tests, for documentation tests, we could also have these with attributes here and do something similar as they do for the user space. Yeah, that's basically it for me. I wanted to leave some time for discussion. There is also tooling. We can also discuss about tooling. I didn't put anything there because I wanted to have some discussion. But there is also other tooling in Rust. We can see if you want this. There is tooling for testing. There is fuzzing libraries. There is MIDI to test unsafe code when you have a test. So it's an interpreter of the intermediate representation. There is also a Rubra, I think it's called, it's a new tool for static analysis. So I can look at the name and put it in the chat later. But this is static analysis. So there are some tools that are appearing also for testing, etc. So there is quite already an ecosystem for Rust on testing. We also had a talk from Alistair Ray from Google on formal tools, and he was using Please to test the abstractions, etc., that we have in the kernel so far. But yeah, the question is how do we turn the mic? There's a button in the bottom middle of the screen. Yeah, so the discussion basically for the experts on testing, etc., I would like to ask you: do you see value on? The main question is: do you see value on using the Rust native way of testing? This is something, basically, having this, and let me put that slide because perhaps it's the most interesting. Having these kind of attributes would take some work, but I think it's reasonable to have, it's not, I think, too much work. We need perhaps to, there is some questions about how do we put it upstream, how do we customize this, but I think it's possible. So if people think it's useful, and the QUnit and self-test maintainers perhaps don't think we are overstepping a bit on the, we are not duplicating, we don't want to duplicate the testing.
So, sorry, I think I think we have to understand what it is that you're proposing first. You know, are you planning to run existing self-tests and KUnit on Rust kernel, or you're proposing writing tests in Rust? I guess I don't fully understand what you're proposing.
Okay, so this will be intended to test Rust code only. So that's the first thing. So this will only test Rust code, of course, or not basically not trying to use this to test C code. So that's so this is only for Rust code. And second, if I understood you correctly, so there is the two kinds of tests I mentioned. One is the documentation tests, is just as a nice feature to test documentation, etc. But then there is all the other tests. So basically, instead of using QUnit and self-test, we will use this on the Rust side instead of writing QUnit tests. And so basically, we will be not using that infrastructure in the Rust side. I don't know if that answers the question, or if you have, please ask me again if I didn't understand the question correctly.
Let's continue the conversation in chat. Looks like Brendan and David are getting ready to do their presentation.
I think we've still got a bit of time, but
yeah, I actually wanted to
to
ask questions about the Rust presentation, but David, you got on first, so.
Yeah, I was just going to say, I think there's sort of almost two halves to this. Do we want to write tests in Rust and test code in Rust? Which I think the answer is almost certainly yes. And then there's, is this exact mechanism of the normal way Rust tests are written the right thing, which, you know, I don't think there's a really good argument against at this point, but it's certainly different from what tests written in C are. As things are from the slide you've got up now, basically the user, you know, the host tests presumably are what you've already got working. The
exactly.
user
Those are the
tests
ones that work. Yeah, exactly.
basically seem to be effectively where k-self-test currently kind of exists. You know, code that runs in user space and then pokes the running kernel. And the kernel ones basically are where KUnit's currently sitting of code.
Yeah, this will be integrated with exactly.
White sort of you know, digging in white box testing. I presume there are ways you could get, you know, Rust to automatically convert these into the appropriate binaries, you know, modules, etc. Programs that, you know, could have a k-self-test sort of wrapper script or something that then run. So I think that's probably sort of one half of it. How do you convert this into something that's automatically?
Yeah, let's assume we can do it. Let's assume we can do it.
Yeah.
So let's like the implementation we may take a while because perhaps we need some features that we may ask upstream, or we need some way to customize these attributes and how the compiler. There is a bunch of things to do. But basically, the main question I think is, if we can do it, would you like to have this? And would you think we are like, is a problem duplicating in a sense? I mean, it's not duplicating in the sense that there is no way to really from C easily test Rust code anyhow. Because of the different languages, if you want to test some types in Rust, etc., it's not really easy to test from Rust, from C, sorry. So if you think this is worth, basically the question is, do you think if this is worth it? This also integrates, as you said, it integrates KUnit, self-test, and the host test all in one.
Yeah, I think that would be great. I mean, when I first started working on KUnit, I really wanted to be able to run KUnit tests as like individual binaries that didn't depend, but basically kind of like your host tests. But I abandoned that idea pretty quickly just because I realized that like there's just the kernel. There's so many dependencies in the kernel, and it's so difficult to isolate them. I mean, I think it would be great if they could be isolated over time, but you do occasionally come across bits and pieces where I think that's doable, and being able to run those as like one of your host tests would be really cool. I think this is really exciting to me, just because I think like, you know, these tests would, you know, if you could get this working, it would be really, really nice for Rust users. But also I think that this is, you know, could kind of compel maybe like a parallel C sort of interface where, you know, I think we've seen like there was one instance where somebody recently posted a KUnit test to the mailing list where it probably should have been a k-self test, but they really seemed like they wanted to write it as a KUnit test because like they liked the interface for KUnit better, but it should have been like, it actually should have been run from user space. And I think that if we had like a consistent interface, then you don't have to pick really. Like you just write the test in the way that makes sense, and then you run it where it makes sense. And those are two decoupled ideas, which I think it would be awesome. So I'm actually I hope you're able to get this working, and I hope we.
Okay, that's great. That's basically great.
Yeah,
that's the answer I could get basically.
Yeah, just as long as we get a parallel C interface out of it.
Yeah. We will need we will need to modify I guess the somehow, if we are going to use attributes in the C side as well, we will need to modify also the C compiler or whatever, or have a plugin for the CC perhaps. I don't know. I don't exactly know, but yeah.
I think sort of the next obvious steps here from my point of view are, so the two problems that need solving are, one, can you write things like KUnit modules from Rust, even if you don't have all this syntactic sugar first, as sort of a, get a test that, can be used as a KUnit test linked into the kernel. Everything's there because KUnit currently requires a few macros for sort of putting things in linker sections and that. Get that sort of stuff working. And then you can look at sort of adding this syntactic sugar on top to automatically generate those. And the second thing is there'll need to be some working out of how do you work out what all of the tests are named from KUnit's point of view. Do you need some way of, grouping them into suites? Do you need some way of being able to put the suite setup?
We could have attributes here, like extra information here. We could have extra information here to put other metadata or suites or grouping, or even grouping by the module, like you saw before. The basis of the module, we could even use modules to group things. I mean, there are different possibilities, but there's also two ways of doing this, like independently of the key unit, etc., which I don't think, of course, you want. Like it's basically creating our own solution for doing this. And then there is the other way, which is generating the key unit test automatically from this code, which is also possible. And we could even do it perhaps with prop macros. I don't know. Prop macros in Rust is basically a program. It's a plugin that compiler compiles on the fly and then runs it inside the compiler. So it's like a plugin for the compiler that is written in Rust and is automatically executed. So perhaps we could also do it like that. But
Speaking of KUnit, it's now time for the KUnit talk. So thanks a lot, Tim.
Thank you for having me here, even with the overload of Rust talks. So thank you for coming as well.
It sounds like the beginning of a really good discussion about how to run tests in a more generic way. Who wants to be presenter first, Brendan or David?
Yeah, we're kind of like switching back and forth. So like there's some sections that
only one person can switch the slides unless.
Okay, well, we actually practice with me like switching the slides, so I'll
Brendan will do that, and I'll yell at him.
Oops.
Yeah.
Okay, now I should be able to switch slides.
Yep. All right. Looks like it. Cool. Okay, there we go. All right. Hi, everyone. My name is Brennan. I'm here with my colleague, David. We work on KUnit, and we're going to be talking about what we've been doing over the last year and what we hope to do in the future to expand KUnit's usage. Whoops, gotten used to hitting the keyboard. So we're going to divide this talk in roughly 4 sections. We're going to talk about just the pure numbers of the growth we've seen in the last year. We're going to talk about some of the blockers and problems that we face that we've tried to address and we're trying to address. Then we're going to talk about some of the features we added in the last year to address some of those problems. But a lot of the problems and issues we're facing right now don't really have technical solutions. So we're going to talk about some of the non-technical growth efforts. So I've been really, really happy to see the amount of growth we've seen last year. We've seen overall about almost a 3 times increase in the amount of tests, depending on whether you measure by individual test files or whether you measure by test cases. But one thing I've been really excited to see is the amount of people who've contributed to a test has increased by over a factor of 5. This is a plot that shows the test cases per release. I think there's a pretty strong linear growth trend here, a lot of momentum there. So that's something that's really exciting. I'm not going to really talk about this slide. People can look at it if you want. We just realized that there's useful information here, but it kind of takes too long to explain.
So there are a number of new KUnit tests that have been introduced in roughly the last year. Again, we're not going to go through all of them for time, but there's a good list. One of the interesting things that you will note is that a lot of these are tests for new features that have been introduced to the kernel, like Daemon, the data access monitor, or parsers of some kind. A lot of the stuff in the Thunderbolt topology, ALSA SOC topology, the fat file system stuff's parser related, or library code of some kind, like the rational number stuff. So interesting stuff, but that tend to be constrained in what areas they are. Next slide, Brennan. So there are basically a number of things that are blocking people from using KUnit or stopping people from immediately deciding KUnit is what they want to use right now. KUnit is basically, as a result of being a unit testing framework, really good at testing isolated library-like code that doesn't have a lot of dependencies. Basically anything pure functional or parsing or the like is really easy to work with. Anything that has a lot of access to global kernel functions, hardware state, is a bit more difficult to work with. And this is generally true of unit testing, because that's not really what unit testing is traditionally about, but it's also what a lot of the kernel is. And that means in the past, architecture hardware-dependent tests have been a little bit more difficult to work with. There's also been just some areas of KUnit that have not handled it perfectly. KUnit tool, which is our wrapper script, has only supported running tests via UML, user mode Linux, but a lot of drivers would not build against UML. Sometimes dependencies for things like multi-core systems that some tests needed were only known about at runtime. And equally, it's been a little bit tricky to actually configure what tests you want to build and run. Particularly, what we want to nice if you trying to test a subsystem or some particular area, you want a quick way of saying run all the tests that are relevant to that. And finally, it's been really tricky for people to work out when you should use KUnit versus when you should use K-self-test versus when you should use either some other framework or just write a module to test your thing. And making that clearer to people, as well as providing feature parity and compatibility with these other test frameworks so that you can pick based on what's best for the test, not based on this supports my weird system better, or I understand the output format here, or this uses tabs instead of spaces and I like it better. It makes sure that people can pick the actual best framework for the job. Next slide.
All right, so now we're going to talk about some of the new features that we've added in the last year to address some of those problems. So the first thing, like David just mentioned, KUnit tool did not support anything outside of UML. To be clear, the core library has always worked against every architecture supported by the kernel since it was merged upstream. But our wrapper script, which we use for automating or making it easier to configure, build, and run tests, has only supported UML just because UML is a much more constrained environment. Arbitrary kernels are not very constrained. But now to address to alleviate some of that pain, we added QEMU support to KUnit tool. And for normal things, it's pretty straightforward to use. All you have to do, it works the same way as KUnit tool normally does. You just have to add these two additional arguments, arc, and specify your toolchain prefix, and it builds your kernel just like it normally would under UML, or configures it, builds it, runs it, and then extracts the results. So we support these architectures currently right out of the box. I think this covers most of the really popular ones. No offense to anyone who's not on this list. If you don't see your architecture here, writing one of these configs is really, really easy to do. There's a number of examples to refer to, but nevertheless, if you'd like to do that, just reach out to us and we'll help you do it, no problem.
So one of the other features that has been added in the last year is support for skipping tests. So again, this is for cases where tests have dependencies or hardware requirements that you can't handle just by adding a dependency to your kconfig entry, particularly things that aren't known until runtime. So the solution to that is, if your test is running and it finds that it no longer makes sense to run this test because, you know, some dependency is not satisfied or something similar, the test can just skip itself. And an example here is KCSAN, the kernel concurrency sanitizer, only really makes sense on an SMP multi-core system. So those tests will skip themselves if you run them on a single core machine. The KTAP specification, which we'll get to, provides a way of outputting tests that are skipped, and this is what K-self-test is used for a while. Next slide. Using the skip test stuff's pretty easy. There's a macro KUnit skip. It prints results out in, you know, a sensible font. It's the same as what K-self-test uses, and if you use the tooling, you get it in a nice color. Next slide. Another thing that we've added support for the KUnit tool is using what we call .kunit config fragments, which is basically a way of specifying a pre-done set of kconfig configurations for testing a particular subsystem or area. So basically, instead of having to go and edit this config file manually, different subsystems can provide a pre-written KUnit config list of dependencies for tests and test configs that need to run. And you can use the kunit.py run KUnit config argument and pass it the directory or the config file, and it will build and configure and run that automatically. Next slide. For a more granular way of looking at tests that you want to run, we're adding support for being able to filter what tests run via a glob. Currently, you can filter by suite. So if you just want to run the example suite, you can use kunit.py run, you know, example star, and it will run every test that starts with a suite that starts with example. If you want to run, say, just the list delete tests, we're adding support. It's being, you know, reviewed, will be in the next version, hopefully, for filtering the tests as well as the suites. So you could glob on the list kunit test dot anything with del in it and get just the linked list deletion tests. This can be run directly from the kernel or via KUnit tool, but it doesn't really make sense if you're using modules, because in that case, you're already just running the things that you are loaded. Next slide. Also, we've added test statistics support. This is basically just a feature parity thing with K-self-test and other test modules. Basically, a lot of test modules and the like printed summaries of how many tests passed, failed, skipped, etc. And while KUnit could do this, it was part of this Python wrapper script KUnit tool rather than part of the in-kernel framework. And so if you were using things as a module or not running it through KUnit tool, you didn't get that, and someone would have to go and count all of the tests manually to get that count. And this was a regression when we were porting tests from you know, random sort of ad hoc test modules to KUnit. Suddenly the output was a little less useful. So we now have output. It's based on something that's the way K-self-test prints out outputs. It's a little bit different to handle nested tests properly, but otherwise, you know, no longer a blocker for people. Next slide.
All right. So one of the other things we've done, this kind of transitioning into the less feature related, less technical things that we've worked on. We've added a, well, I should say David added a kernel testing guide, which currently it tries to delineate some of the cases where you should use KUnit versus K-self-test. It's not exhaustive, but it's a good start. We're hoping that we can, and other people will expand this over time and also include testing tools other than KUnit and K-self-test to create basically in the future a comprehensive guide where if someone wants to test some code for the kernel, they go there and it tells them either what to do or where to look for further information. We also have a tech writer working on improving our KUnit documentation. So now we're going to talk about some of the other non-technical things we've been trying to do to grow KUnit's adoption.
So one of these things, and quite a big and important thing that's come up a little bit earlier today, is what we call KTAP standardization. Basically, both KUnit and K-self-test and a few other things are using variants on TAP, which is the test anything protocol, as a format for test results. And TAP is pretty sparse, originally intended for Perl stuff, didn't really provide everything that we needed for kernel testing. In particular, we wanted to have nested test support. TAP originally didn't want to support that. K-self-test and KUnit, for reasons that seemed sensible at the time, sort of implemented these slightly differently and in incompatible ways. So tools like KUnit tool in particular really could only parse the exact result format that KUnit could provide. And what we want, and what people like Tim Burton that have started, is to standardize a kernel variation of TAP for in-kernel and certainly in-kernel tree tests, so that we can share tooling much more. And basically the idea is any parser should be able to handle K-self-test and KUnit results basically indistinguishably. We've had Ray, one of our interns, working to rework the KUnit tool parser to support some of the things that KUnit doesn't use, but K-self-test does. And she's also helped sort of get the ball rolling a bit again with some of the standardization work, which has been a bit stop-start over the last year. Next slide.
So like David mentioned, with Ray, we've also been hosting interns, and not in the past year, but also LKMP mentees. Since the start of KUnit, we've hosted 12, including all interns and LKMP mentees. We've only hosted 2 in the last year, but I wanted to mention the LKMP mentees because of the next slide. But of course, it's always good to have interns working on the kernel, because it promotes kernel development and open source development to the next generation of engineers. But also, we're kind of hoping to, somewhat indoctrinate them with the good testing practices when and hopefully they become full-time software engineers. On a related note, we also presented at the Linux Foundation Mentorship Series, which is another talk series that's kind of targeted at new software engineers who are just starting working on the Linux kernel. So like I mentioned, the LKMP mentee, I wanted to specifically call that out because one thing I was really excited to see, that a group of students organized a KUnit hackathon, and they did this totally of their own volition. But one thing I noticed was that one of our former LKMP mentees was there, and I suspect that's not a coincidence. So that was a really, really cool thing to see. And I'm really in particular excited about that. And I think we're all pretty happy with what we saw them do so far. But they seem to think that it worked out well for them as well, and they're planning on doing another hackathon in the future. They wanted to do some things other than test conversion, so we introduced them to the DRM subsystem maintainer, Daniel Vetter, and it seems like there's some strong potential that there might be a hackathon where they're going to work on some DRM subsystem tests. So it'd be great if we can do work on other subsystems in the future as well, or sorry, they can work on some other subsystems as well in their hackathons. So if anyone has any subsystems you would like to have some student hackers work on your help develop some tests for you, you should reach out, and I'll put them in contact. And it actually looks like we have one of them in the chat, so you can probably reach out to Andre.
So one of the final things we want to talk about is faking and mocking, and basically how we handle testing code with hardware or complex dependencies. Is a theme throughout this is difficult, and this is also one of the things that everyone seems to immediately go, this is why I can't test my driver. And in general, the solution for this with unit testing is that you replace the dependencies or hardware or whatever with fakes of some kind. So instead of talking to real hardware, you implement basically a fake device which will respond in a certain way depending on the test. And you can have several of these ones that, always errors, or one that actually sort of emulates the device a bit more thoroughly. And similarly, global functions, allocation functions trying to read files or read blocks from block devices. These are things that a lot of the code in the kernel, directly needs to call these functions, and it's very difficult to totally remove them and replace them because you need them for the kernel to run. But at the same time, you want to be able to sort of intercept that and say, hey, I'm trying to test, file system parsing. I need some way of intercepting a block device read, or refactoring code so that I don't need to intercept a block device read. We've written, one of our colleagues, Daniel's written a great doc on sort of different ways you can intercept functions on the KUnit website at that link. But one of the things we've tried in the past is implementing a sort of more full mocking framework, and just with the way C and kernel development works, it's not trivial to do this in a way that's actually useful in all of the cases people expect it's going to be useful. So that's kind of on hold at the moment. And really what we've discovered is most subsystems and areas you need to write bespoke sort of fake devices or fake implementations, and then maybe we can work out that some of them will be useful to share between more devices. So next slide. One of the things that we're starting to do and looking into doing is trying to find subsystems and drivers and file systems and the like, where we and others can go and basically say, okay, we can test library-like code really easily. Let's chip away at these and start trying to test the more difficult bits rather than just going after the easy parts. So one of the ideas here is taking, say, for example, ext4 or another file system where we've already got, tests for timestamp conversion, which is, very independent, and working out, okay, how do we test the more complicated and trickier bits? Like, do we need to write fake inode structures or fake superblocks, or have a fake way of reading blocks from the block device? Or is it better to make more elaborate fake things here? Or is it better to refactor the code so that instead of calling these functions, it accepts things more as an argument and it's easier to test? So that's something we're looking to do. We've got some experiments on local machines that haven't got very far yet, and certainly interested to see what people think of that. And with that, we'll open the floor up to discussion, because what has it been that's stopped people from writing KUnit tests, or been difficult, or questions you don't have answers to? And does this seem like a sensible path? Have we done the right thing, wrong thing? What do you think?
So I put some, oh, cool, we got someone. Guillaume, it sounds like you're muted.
It was a hardware mute. Sorry, look, yeah, of course I'm interested in having this running in kernel CI, and thanks to your work, it's 80% done. There's still a few things missing. But I wonder if other systems are running KUnit automatically, because adding a KUnit test, if people run it manually, it's useful, but if there's some system somewhere that runs it automatically and reports issues, that's even more useful.
So LKFT is running KUnit tests. under QEMU for x86 and ARM64. So those are being run automatically, including some of the ones like the KA-SAN tests that can't run under UML at the moment.
We also have like a little kind of experimental thing that uploads patches sent to the K-self test list to Garrett, and we run KUnit tests as pre-submit against that Garrett instance as well.
And do you think there's anything else in this space that could be done to provide an incentive for people to add more tests? Because if something breaks, it becomes more visible if the errors are reported directly. I don't
know. So sorry. Which part? Like, what part are you saying should be more visible?
If tests are run automatically, like if LKFT is running KUnit automatically and an error is found, then it's more publicly visible, and so it has a bigger impact than if a test is there, it relies on people to do it by hand. So do you think there's more that can be done in this area to run it more or share the results more?
Yeah, probably. I think that right now, like getting the test configured to run is kind of a pain. LKFT sets an option which I think it's called KUnit test all. I forget the exact name off the top of my head, but most KUnit tests enable it. And if all the dependencies for the test are satisfied and that option is selected, the test will automatically be turned on. So basically all you have to, as long as the dependencies for your test are enabled in a kernel, it'll run on LKFT. But of course, LKFT, they care about x86 and ARM. So if your test doesn't run on one of those architectures, then it's not going to get run. And so I think there's a lot more work that could probably be done there to make sure your tests actually run. But I think it's hard because that basically means everyone has to create like their own config. And I don't know that this is something that'll happen in the short term, but maybe the subsystem configs that David mentioned earlier in the talk could hopefully maybe help with that in some way.
Yeah, one thing on that front that we'd really like is for subsystem maintainers and the like to be able to say, hey, look, this is the .kunit config for our subsystem. When code is submitted, you should run it against this. We will run it against this when testing it. And you should, if you write tests that are enabled by that, we know they'll be getting run.
Okay.
I see there's a discussion in the chat around adding basically expectations for demessage output and sort of intercepting it and expecting certain things to be printed on the console. So that's something that, a couple of tests have looked into doing and doing. In general, I think there's a sort of idea here of we don't want to add things to the KUnit framework until we're sure there are users, and ideally more than one user. So it sounds like, there are multiple people using this, and merging it in will probably, that's a good start for, maybe this should be something that we include as part of KUnit or in a common place for tests to use. But it's equally easy to get burnt by, having to write a new feature generically for everything rather than get your test working. We can always factor things out later.
Just wanted to say it's normally the end of the microconf now, so I guess people can still carry on talking, but I wanted to say thanks to all the presenters we had today. And of course, tomorrow we have a related topic, microconference about called kernel dependability and assurance. And I have to say the difference between that and this microconf is a bit fuzzy to me. So we'll be talking about more testing things tomorrow. Sasha, is there anything you wanted to add?
I just wanted to thank all the folks who presented here and participated. It was another great year, and hopefully we'll meet in person next year. We'll see.
So
folks
I
are free
think
to stay here and keep discussing. It's not nothing that true.
Yeah, the server is not going to shut down anytime soon, so it's fine.
Yeah, I think David and I are able to hang around. I mean, I certainly am. If anyone wants to give any further suggestions or advice or complaints or concerns about KUnit, or particularly ideally around things we could do to help make it easier and grow the user base. But
yeah, if get worded. So I tried use. It's been since I looked at it, but I tried using KUnit for RegMap and found it was fairly laborious to do anything with it. It's been a while, but I think the main issues I had were working out how to expose the internals of the API to the unit tests and not to anybody else. So I didn't get people doing things with the attractions. And also, I couldn't work out a nice way to set up test fixtures. It didn't seem like KUnit was really helping me with that. I was having to open code it. That might have changed because it was quite, or one or both of those might have changed. It was quite a while ago that I did this. But yeah, it just felt like a lot of work to get the coverage I was looking for that sort of in binary testing.
Yeah, and on the first point, it's partly just one of the realities of working with C in the kernel, that it can be really awkward to try to expose functions to just your tests in a way that's not ugly. So we have some solutions to that, but they're all ugly in some way.
Yeah.
The
yeah,
page...
I don't know if it's like I think part of what I was thinking there was that having a way of annotating things, like even if it wasn't like technically hidden from anything, just a way of annotating things that would scream at people or something, or at least jump out somehow, that it was supposed to be for KUnit. But it felt like I was having to freelance on that, and there wasn't anything that KUnit was helping me annotate.
Yeah, at this point, basically what we've been doing is either, you include your tests basically directly in the same file so that they can access, static functions, or you have a whole bunch of custom, if-def config whatever test, or sometimes config KUnit define whatever, static, or define whatever nothing, as a way of doing that, which, it is a bit ugly. It's one of those things, again, where there are few enough tests already doing this that, we haven't seen to some extent that need. But certainly there's not one solution to this that fits everyone, which works. But we'll definitely take it on board.
I did send out a patch at some point. We didn't merge it because there wasn't anyone who looked like they wanted to use it, but it does basically what David just described, where it's basically a macro that replaces static on functions, and the function is basically static if KUnit is not present, and it is not static if it is present. So it basically allows you to export a function outside of a compilation unit only if you're going to test it, but it's pretty ugly. And it seemed like at the time the only motivating use case they were more amenable to just having us include the tests directly in their in the file that they were testing. But yeah, I mean, if that's I don't know if that would help you in any way. To address the second part of your problem, what was the second part again?
Fixtures.
Test fixtures. You didn't find that the test init test was it clean out or is it tear down? In the test suite, like fulfilled that need?
No, I can't. Are those per test or are they?
They're per test.
Yeah, I think it was wanting to reuse the thing over multiple tests was part of the issue.
Yeah, we had somebody suggest a patch which would set it up at the start of a test suite and then tear it down at the end of the test suite, so you could reuse things like what you suggested. But that patch set didn't go in, and because he was the only user of that feature, it didn't go in. So, again, if that's a feature that people want, it would be a pretty trivial to just go and find that patch and merge it in.
Something like that would help, or like even being able to do that on a more fine-grained bit with groups of tests. Like here I will test feature X. Here I will make a dummy feature X to test it with. Now I'll run the test. Now I'll stop running the tests. But that extra level might be more trouble than it's worth, because it's only really saving you a bit of memory rather than anything else.
Yeah, one of the sort of conflicts there is ideally you want the tests to be as independent as possible, so that effectively you can skip tests or do the like without having global state that can be mutated by several tests and the order that they run suddenly matters or the like. So it's sort of something that we've not really put a lot of thought into that's how the sort of system's designed. But there are definitely cases where it's much more convenient, and we do note that.
Yeah, I mean, you could always, if you had a way of say something like here are the creation and destruction functions for this group of tests, and then you could always just run the creation and destruction function before and after every test. Like the thing, it was the repetitiveness that was an issue more than and having a way to pass the state into the test more than the.
So like as a performance or memory use or whatever thing, or.
It was more like I was having to specify the same thing over and over and over, or do the same thing over and over and over again.
Yeah, I mean. We'd hope most cases that'd sort of be handled by the suite initialization and shutdown functions, and you just make several suites, which you can do quite easily within the same file. And there are downsides to having lots of suites in terms of okay, now you've suddenly got a whole bunch of different suites that might not be the way you wanted to organize things. But on the whole, that's a pretty reasonable way of doing it.
Yeah, I think I was using suites for something else already. So I think I wanted to nest it 2 layers. Was the it's been a while, and I think I threw away the patches because they're a bit rotted. But I think the issue I was having was that they were with that was that it was I wanted 2 layers of things.
Yeah, we've been edging a little bit further towards allowing more interesting levels of nesting. One of the new features that we haven't mentioned during the talk is parameterized testing, where you can run the same test function with a bunch of different arguments, and that sort of acts kind of like an extra layer. The KTAP standardization stuff and reworking around the tools there, one of the major part of there is making sure much of the KUnit stack actually has this concept of more arbitrarily nested tests, so that, you know, if that becomes useful, you know, it's something we can support more. But in a lot of cases, again, you know, you can just use test init, you know, splitting things up into more smaller suites and just naming the suites something that makes it obvious that they're related has been the sort of go-to thing in a lot of cases that's worked in many situations. And you can have several suites in the same test module and same config option, which sort of is kind of a level of nesting, even if it's not in the result format. But we'll definitely note it.
So I can get back to you about what the more concretely about was. But it sounds like the one or both, or, you know, some of those ideas might help move forward a bit.
Yeah,
I think some of those things are new since I looked at it, 'cause it was very early on that I looked at it.
yeah, a few things on that front have changed, but I think, yeah, certainly the parameterized testing stuff, and that's needed. Okay.
Yeah. So I was while you were discussing that, I was responding to Ira asked about the static thing. Is there anyone else who would find the visible for testing macro useful? It just seemed like in the past everyone was okay. Everyone who had that situation was okay with having the KUnit tests just included within, optionally included within the compilation unit that contained the static functions. So I think, to be clear, it sounds like that's kind of the preferred mode that Rust wants to take.
And the problem with doing that is you don't end up with a separate module for your tests if you want to do things with modules.
Right.
And on the other hand, the problem with doing this sort of visible for testing macro is that's either static or not, is you still need to have the function declaration somewhere, so the signature, so that your test code can access it, which for a static function you might not have otherwise bothered doing, or putting in some public place. So you need to have an extra copy of that. There is no really nice solution to this problem, and there's no reason equally we can't have both solutions available.
Right. We've just had some features. Well, actually, I think at this point, all the features that we've added have pretty much been used. But I mean, there are definitely like some features that I think like only one person uses that, and
it's a chicken and egg problem of,
yeah,
you know, you don't want to add these things and then have no one use them, because it's silly just having patches that add macros that no one uses.
Yeah.
But no one writes the test that would use it if it's not already there. So definitely, if you've got tests where this sort of thing is necessary, either write it yourself, drop it in your, you know, add it as part of the test. It's, you know, something like this we'd be more than happy to add, or reach out to us and we can sort of coordinate and get these things in.
Yeah, but I think in these cases, both the things that Mark brought up, I think it seems like there's probably enough interest, because I think they've been brought up a couple of times. So I think we should probably just add those in now, especially since the patch already exists. Anything else anyone wants to discuss? Also, thanks for sharing that example, Ira. That looks that was, yeah, seems like a very similar situation. I saw somebody, I think it was Felicitas, started to type something. Is there anything else anyone wants to discuss? Say, give it 30 seconds. If anyone wants to discuss anything, speak now, or I think we'll
Or just
head out.
talk in the chat or send an email at some point.
Right. I mean, yeah, this is going to be open, I think, and there's plenty of people who are here. So, well, that's a good question. I don't know. Can I, since I have presentation ability, can I add somebody else as a presenter? Manage presentations. Oh. Okay, it'll let me select presentations, but it won't let me add new presenters. Maybe. Who's
Yeah,
the
I
person
think
who said that?
wasn't supposed to work, but
Well, I'm gonna pick on David then and experiment, see if I can make you. I can give you whiteboard access.
exciting.
I guess.
Oh wow.
Yeah.
Okay, we're just gonna keep playing with the big blue button until we break it, unless people have actual questions. So.
Yeah, I clicked on David, and it just, the only option I have is give whiteboard access. I can give you whiteboard access too.
Doesn't appear to have done anything on my end, but
Okay. Settings. Maybe it's because I didn't set this up. It looks like there are people. You might be able to go to the main chat room, the element chat matrix element, whatever you want to call it, chat room. They might be able to grant you presentation there. Oh, on the left side. Yeah, right. I'm on the left side. And you said it's, you click over the person's name. No, I don't know. Sorry. In any case, it's after lunchtime for me. So, oh, looks like Jonathan's in the room, and I saw he was given in the main element chat room. He did something with whiteboard access. He might know what to do. I guess he's not listening. All right. Well, anyway, I'm going to head out. So anyone else here, feel free to chat. Sorry, I wasn't able to give grant presentation abilities to someone else. Oh, I wonder if I take no. Okay. All right. Well, anyway, I'm going to head out. Hey, everyone.
yeah, thank you everyone, and do feel free to reach out either through this or email at the KUnit or K-Self-Test mailing lists, and we'll monitor those and answer any questions you have.